Test, test. 1, 2, 3. 1, 2, 3. Teste, teste. 1, 2, 3. 1, 2, 3. Test. Test.
It's starting to work. It just shows connected around. Test, test.
Oh, also for the speakers, you should kind of like get up and switch at the 1 minute before as the last speaker is answering questions. So 1 minute before your time. Okay. So just kind of come up and swap. Yeah, ask the student volunteer. So the second speaker can get.
Okay, let's start. Good morning, everyone. I'm Jingzhu. Today, I'm going to present our work, Alimus. SSIF vulnerabilities are inevitable in PHP web applications. These applications often use server-side requests to communicate with third-party services. However, the attackers can exploit this by making it look like the server itself is sending the request, allowing them to bypass access controls like firewalls that normally block direct access to certain URLs. Exploitation of SSIF vulnerabilities can lead to severe consequences. For example, in 2019, an SSIF vulnerability in Capital One's service led to the exposure of credit card information for over 100 million customers. Since 2021, SSIF has been ranked as the top 10 vulnerability by OOPSLA. Currently, PHP is the dominant programming language for building web applications, and developers have limited experience to avoid SSIFs. Static 10 analysis is commonly used to detect vulnerabilities in PHP web applications. To illustrate the idea, let's look at a new SSIF vulnerability. The application takes the user input from the post function, and we mark it as a source. This input eventually reaches the request sending function curSetOpt, which we treated as a sink. Our goal is to determine whether there's a feasible path from the tainted source to the sink. However, the analysis becomes tricky because the call flow is hidden by a dynamically assigned class name, RSS file class. Existing static tools fail to build a complete call graph. Another issue is that these tools often ignore path conditions inside if statements. In this case, a feasible path only exists when URL variable is not empty and contains the substring block spot. We observe 4 key challenges in the existing tools. First, third-party sources and sinks are ignored. Second, both explicit and implicit call targets are used in PHP applications. Third, there exists either over-tainting and under-tainting rules. Fourth, infeasible paths are reported because of ignoring path conditions. In our paper, we design and implement a new static taint analysis tool called Artemis to detect SSIF vulnerabilities in PHP applications. Artemis has 4 modules. First, it extracts both PHP's built-in and third-party sources and sinks. Second, it builds explicit and implicit call graphs while handling PHP's dynamic typing. Third, it performs taint analysis to find possible paths from sources to sinks, using enhanced propagation rules. Finally, Artemis reduces false positives by analyzing path conditions and removing any infeasible paths. For source and sink identification, Artemis identifies them from both PHP's built-in and third-party libraries. We identify built-in sources and sinks following previous work. For example, we treat get and post as sources because they typically take user input from incoming requests. For built-in sinks, we include functions that access files or send network requests. For third-party sources and sinks, Artemis focuses on public functions with PHP doc comments because those functions are intended for external use. Then, we use few-shot learning with GPT-4o to classify whether each function is a source, a sink, or neither. To make sure the results are accurate, we manually verify the extracted sources and sinks. To statically construct a call graph, Artemis identifies both explicit and implicit call targets. For explicit call targets, Artemis matches method call signatures. Specifically, we look at the class name, the method name, and the parameter counts and types. The last 4 call types correspond to implicit call targets. When the method and class name are known but the method isn't defined in the class hierarchy, Artemis treats it as a magic call and searches for PHP's magic method. Specifically, we check call and call static along the inheritance chain. For example, the method call client wrapper get doesn't match any defined method in the client wrapper class. However, since the call static method exists, Artemis recognizes this as a magic call and builds the corresponding call flow. When a call target has a known method name but a variable class name, Artemis searches through all built-in and application classes to find the method with the same method name and the same parameter count. If no matching method is found but the class defines the magic method, Artemis treats the magic method as a possible call site, regardless of its parameters. When a call target has a known class name but a variable method name, Artemis searches all methods in that class and its class hierarchy. Any method with the same parameter count is treated as a potential call target. Moreover, all magic methods in those classes are considered candidate call sites. When both the class name and method name are variable, Artemis searches all methods across all built-in and application classes. It looks for the method with the same parameter count and compatible types. Moreover, Alimus considers magic methods without parameter checking. Third, Alimus performs rule-based TAN analysis to track how tainted data flows through the core graph. We design a set of propagation rules to handle common PHP operations. To improve accuracy, these rules are carefully designed to reduce both over-tainting and under-tainting. For general cases like variable assignment, unary or binary operation, and typecasting, Alimus follows the same rule used in state-of-the-art approaches. When Alimus encounters a branch like an if-else statement, it uses a fine assignment rule to merge the states coming from different branches. When a method is called, the program's state moves from the argument to the method's parameter, flows through the method's statements, and then returns to the caller via the result. When initializing an array, Alimus records every element's state based on whether the index is known. It tracks individual elements, not whole arrays. When Alimus says a for each loop, it marks the loop variable as tainted if every element in the array is tainted, or if the array is partially tainted but the loop body has no branch. For example, the array URLs comes from post, which is a tainted source, so URL is tainted. Inside the loop, image URL is created from URLs, so it's also tainted. We also handle implicit data flows that arise from PHP's dynamic features. For instance, the built-in extract function creates variable from an array. When Alimus says extract, it synthesizes explicit assignments so the data flow is tracked. Finally, to prevent over-tainting, Alimus uses safety string assurance. A string is only considered tainted if it can actually control the file or request the URL an attacker could use. So, if a variable controls the IP or requests the URL, it's tainted. Otherwise, it remains untainted. So far, the rule-based TAN analysis is path insensitive, which can produce false positives by reporting invisible paths. The fourth module helps reduce this by pruning two types of false positives, which are always unsatisfied conditions and URL rejection conditions. Given a tained propagation path, Alimus extracts path conditions from each function or method's control flow graph. It then prunes unreachable paths because their conditions are never satisfied. For example, if the variable service has mismatched values which are max-min and fragile IP, Alimus recognizes this as a false positive. Alimus also prunes false positives caused by string checking conditions. To do this, it first identifies common string checking functions like strpos and pragmatch, and translates these checks into string conditions. Then it uses an SMT solver to see if any valid URLs can satisfy all the constraints. For example, if a path uses strpos to check a string, Alimus models this as a constraint and also models valid URLs with regular expression. The SMT solver can then show that no valid URL can satisfy all the constraints, so the path is marked as a false positive. We have implemented a prototype of Alimus. For the benchmark, we select 250 applications based on two criteria. First, we collect 55 vulnerable applications from the CVE database to evaluate whether Alimus is able to detect known vulnerabilities. Second, we gather 195 popular applications to assess Alimus' ability to detect new vulnerabilities. We compare Alimus with 5 static TAN analysis tools for PHP. In total, Alimus identifies 207 true positive paths, corresponding to 106 true positive vulnerabilities. Among the 106 vulnerabilities, 35 are newly discovered. We have reported them to developers, and 24 have been assigned with CVE IDs. The evaluation results also show that Artemis significantly outperforms existing tools in both true positives and false positives. To evaluate the impact of each component in Artemis, we conduct an ablation study, systematically removing one module at a time to see how it affects detection performance. All the key results are highlighted here. To conclude, we present Artemis, a static intent analysis tool for detecting SSIF vulnerabilities in PHP web applications. Artemis has 4 modules that work together to improve true positive detection while reducing false positives. In our evaluation, Artemis discovers 207 true positive paths corresponding to 106 vulnerabilities, including 35 newly discovered ones. That's all for my talk. Thank you for your attention.
Get the floor started, warm up those questions. Really impressive, sort of complete work on like these PHP vulnerabilities, and certainly very important with these new CVEs. I wonder if you could talk a little bit about the lessons that you might have learned that could make this more applicable to other languages, or how much of what you've done here is very specific to PHP, how much are lessons that we can take to other languages?
Yeah, very good question. Actually, in our work, some modules are specific to PHP language, like the core graph construction, because the PHP has some dynamic features like magic methods. Actually, maybe in other dynamic languages, they also exist some similar features. We will investigate them in the future. Let's say whether those features can lead to severe vulnerabilities like that. And also, some features are specific to SSIF vulnerabilities only, like the modules like we do the false positives. I believe that this framework is not so specific, and we can extend such similar frameworks to other languages, to other vulnerabilities, and to build secure software systems.
I had a quick question. Good talk. It's a good tool, it seems. So the source sync identification that you are doing using the LLMs, what if the LLM finds an invalid source sync pair?
Invalid source and sync pair. We don't care about the pair. We only care about whether the sources are true sources and whether the syncs are true syncs. We don't care about the pair.
Invalid source or an invalid sync?
We manually verified. So after we use GPT-4o, actually there contains only a few false positives, maybe 2, 3, something like that. In total, we have, as I remember, we have 42 sources and 40 syncs. Those sources and syncs, we have carefully manually verified them. Yeah. Thank you.
Next up, we have, lost your slides. Well, I'll go ahead and
Thank you for the introduction. So let's start with looking at the general computational stack. So software runs on operating systems which operate on hardware. Performance, especially the performance of the input-output operations, or I/O, is crucial at all levels. The hardware community developed modern hardware such as persistent memory, or new NIC cards that reduce I/O latency. And the operating system community has proposed advanced file systems that avoid redundant I/O. So to maximize the benefits from these infrastructures, it is important to use them in the right ways. So our research focuses on adapting user applications in response to the advances in the operating systems, especially with I/O tasks that involve file or network data exchange. These tasks are prevalent in modern applications. So when the underlying computational models evolve, how do we adapt applications to efficiently use these new I/O interfaces? So let's see why some existing interfaces like read, write, open need updating. These POSIX interfaces are essential for many applications, like web servers and email clients, but they are outdated due to the advances in computational speed and capacity, which makes the original assumptions, such as that the memory is significantly faster than I/O devices, no longer hold. So today, the operating system community suggests replacing them with modern I/O interfaces, like get, put, pig, which we will discuss soon. So these new APIs can make applications run faster. So we aim to automate the migration across different I/O APIs while providing correctness guarantees. So our system is called SPLASH'. It takes a specification from the API experts and an existing program that uses old APIs, then synthesizes a migrated program, then uses the new APIs. We next talk about how SPLASH' removes old APIs from the existing program. And this process has been difficult due to three main challenges: the semantic mismatch, complex control flows, and program state interdependence. I'll explain these challenges and how we address them. The first challenge is the semantic mismatch between different APIs. For example, the read API copies a certain amount of data and updates the file offset. We may want to migrate a program to use the get API, which copies an entire file content. But these two APIs differ. So to address this challenge, we break down APIs into atomic operations to help us reason about the semantics of APIs that are similar but not identical. For example, the get API semantics consists of connect file, transfer, and disconnect. So if we were to replace the pread API by get, we would need to remove the code that performs connect file and disconnect. And another important concept is the semantic types. So programs using I/O APIs often have variables that fall into distinct and well-defined categories, such as file descriptor, offset, and size transferred. We attach semantic types to the variables according to how they interact with I/O APIs. For instance, we attach the semantic type size transferred to the return variable of the function that performs transfer. So each atomic operation emits an I/O behavior. For example, these two code snippets use different APIs but emit the same I/O behaviors. So they are behaviorally equivalent. The code on the left uses POSIX APIs, open, pread, and close, and the code on the right uses the get API. We see two programs are behaviorally equivalent if every pass in one program is equivalent to a pass in the other program. The loops are unrolled only once. So the next question is, how do we ensure a pass behavior remains the same after migrating to a new API? So we construct the finite state machine for each new API. So here's the state machine for the get API. It starts at the state S0 and takes a connect file operation subject to the requirement that file permissions include read access. It next takes a transfer operation and a disconnect operation subject to their requirements. Then it reaches the final accepted state S3. So accept means that the statements on the pass are behaviorally equivalent to the new API. So another challenge is that the real-world programs often have complex control flows with branches, loops, and multiple calling contexts. But multiple related API calls may be scattered in different locations. So we need to simplify the program structures. For example, to handle the multiple calling contexts, we introduced the concept of alias function for intra-procedural analysis while preserving external calling information. For instance, the XM open function is aliased with open because it simply calls open as long as a specific condition is met. So we call this condition a lift-up condition because it is based solely on a parameter and can be handled in the caller function. Thus, we can bypass analyzing the body of the XM open function while still preserving its semantics. The third challenge is the interference from various statements and interdependent variables. For example, here we may want to migrate the calls to APS 1, 2, and 3. However, the input parameter of the APS 3 depends on computations in the middle. So to determine whether these sequences can be migrated, an in-depth analysis of the program states is needed. So we perform I/O state inference backed by flow and field sensitive point analysis to automatically infer program states. We formulate the intermediate state that contains points to results, semantic type maps, file offsets, and loop contexts. And we formalize the inference rules in the paper. Due to time constraints, here we illustrate it in an example. So here, the top left color is the specification, and the top right is the state machine for the gate API. The bottom left is a C program that we plan to migrate. And in the bottom right, we will be updating the intermediate state during our analysis. So the program invokes a set of old APIs. For example, the call to the XM open function contains 3 IR statements, a node, a call, and a store statements. So first, the node statement updates the points to relations by making the variable SS1 point to the abstract object O1. Next, the call statement returns a value and assigns semantic types based on the spec. Because the specification says that the specification says that the API performs connect file. So the return type becomes file descriptor and the parameter becomes file path. This result enables a transition from state S0 to S1 in the state machine. So finally, the store statement also updates the points to relations. And for the call to the read API, the process is similar. I'm going to skip the animation because it's similar to the previous slide. But the point is that we update the points to results and semantic type map, leading to a state transition from S1 to S2 in the state machine. Similarly, for the call to the close API, we also update the intermediate state, then transition the state machine from S2 to S3 according to the spec. So after the analysis, we obtain the intermediate state as on the right. So from here, we extract the semantic types into the semantic variable context as on the left. So we next use these results to synthesize the new migrated program. So first, we remove the minimal code fragments that cause the state machine to transition to the final state. Then we insert a sketch of the new API and the call side to read. Next, we complete the sketch according to their semantic types. But before the code compiles, we need to propagate the effects of the deprecated variable fd. So next, we trace the impact of removing the variable fd through value flows and find 2 related statements and then need to be removed. For example, here we need to find a replacement for the removed statement. We find that the IO function stat is behaviorally equivalent to the function fstat. So we insert the sketch for stat function and fuse the host again based on the semantic types. Once the synthesis is completed, we get a migrated program that is behaviorally equivalent to the original one. So our algorithm is sound. In other words, whenever Sprout produces a migrated program, the migrated program has the same behavior as the original one. Our benchmarks range from hundreds to hundreds of thousands of lines of code, averaging about 10,000. And Sprout identified an average of 202 variables with semantic types per benchmark. And the average migration time is 154 seconds. So we also evaluated how much faster the migrating programs run. We use the new hardware such as NVM, emulated by DRAM within a virtual machine. The average performance gain was 38% per benchmark. Please refer to the paper for further details. So here's the, in conclusion, we present a novel approach to the API migration by addressing 3 key challenges. I'm happy to take questions.
Questions?
Hi, thanks for the talk. So your evaluation looks quite impressive. I was curious if you submitted any pull requests to these projects to actually migrate the APIs based on the results of your tool?
Sorry?
I was curious, so it seems like your work has very big practical applicability to migrate these APIs. Do these APIs actually exist in the sense that you could create pull requests for these tools for certain like real-world programs?
Yes, these are real-world programs. The APIs are real-world too. So the APIs are connected from the papers published in some system conference, such as the SOSP, OSDI. So, yes.
Okay, so I guess specifically my question is, did you consider making pull requests to projects to like update with your refactored code?
Yeah.
Or we can discuss maybe later. Yeah, thank you.
Hi. I was wondering if your high-level approach is also applicable, is also generalizable. Like, do you have any thoughts about that? Like,
yes, we have a section talking about the generalization in the paper, and we generalize to the database domain. We have extra experiments on there.
to which domain?
Database. The database APIs.
Okay,
domain.
databases. So, but I guess you believe that in general, the approach should be generalizable to any particular domain.
So it's all about the specification as a state machine. So if your APIs can be broken down into the atomic operations, and you can define your own state machine to ensure the soundness. So, yeah.
Perfect. Thank you.
Thanks for introducing. Hello everyone, I'm Qiao Lian from Peking University. Today, I'm going to talk about automatic linear resource-bound analysis for Rust via prophecy potential. This is a joint work with my advisor, Li Wang. So, I will first give a simple introduction to Rust. Rust is a popular system programming language renowned for its unique capability of memory management. It provides precise and safe memory control without requiring garbage collection. To ensure memory safety, preventing issues like dangling reference, Rust employs a sophisticated type system that performs static checks at compile time. Compile time, instead of runtime checking, enables programmers to write reliable and efficient code. While zero-cost abstraction like this, Rust targets high runtime performance of programs. The Rust compiler checks the memory safety of programs. However, memory safety does not naturally guarantee good performance. WASP programmer may write memory-safe but poorly performing programs. Resource analysts, especially the automatic one, helps WASP programmers understand the performance of their code. By comparing the results with their expectation, programmer can gain confidence in code's efficiency or identify opportunities for optimization. This is why we want to do resource analysis for WASP programs. To do resource analysis, we will introduce a prior work on resource analysis, the approach called ARA, Automatic Amortized Resource Analysis. The second A is the amortized, which indicates that ARA uses potential method. Suppose we have a program with full and bar and 3 program states. ARA associates each program state with potential information. When ARA system checks the program, it will collect constraints between the resource consumption and the potentials. For example, we define a recursive function over a list of integers in WASP to calculate the sum of all integers in a list. We plot the control flow graph on the right, where S0 through S4 identify program location highlighted in the program. The tick statement in the cons case specify a cost metric that each recursive call consumes 10 units of resource. ARA extends data types with symbolic potential according to their structures. In our example, we have a single numeric symbol P for the list type, which means that every cons carries P units of potential. So the potential of a list should equal P times its length. Different states could have different potential, so we use P0 through P4 to denote symbolic potential of L at different states. ARA collects constraints among those symbols. For example, ARA collects 1 when checking the statement between the state S1 and S3, the cons case, which tells the potential difference should be at least 10th. With all constraints collected, ARA uses a constraint solver to solve these constraints to assign concrete numbers for those P's. In this case, it assigns 10 to the P0, which means that the resource usage of the sum function is upper bounded by 10 times the length of the input list. So when we apply ARA to WASP, we will encounter several challenges. One primary issue lies in defining the potential of the multiple reference. We illustrate this with an example. It creates a multiple reference to the list. The program can be described in 2 states, S0 before the reference is created and S1 after. At S0, there is a single variable, L, and it carries some amount of potential. At S1, there are 2 variables, one L and then another the reference P. Since the operation solely involves creating a reference to L, it seems that the potential of L should remain unchanged. As for the resource of the mutable reference P, a natural intuition suggests that P should carry the same potential as L, since referencing the potential of L can access the original variable L. However, this approach violates an important invariant. The total potential should be conserved. Simply summing up the potentials of each variable at S1 will introduce additional potential. In this example, exactly it doubled the potential. So, to address the challenge outlined above, we leverage the WASP type system, which enforces that the middle reference is exclusive. Returning to the example, after creating the reference P, and before it is dropped, that is, during the lifetime of P, the original variable L becomes temporarily inaccessible. We cannot assign to L. Otherwise, the WAS compiler will complain that you cannot do this. The exclusivity leads to a natural intuition. The potential of the list L is transferred to the reference P, as illustrated in the animation. But then another problem is that when the lifetime of P ends, the potential should be returned to L for the WAS computation. Even the relation here between L and P is simple, but in general, it is not compositional to check the reference relations. Therefore, we propose our key contribution, the notion of prophecy potential. It is termed prophecy because it anticipated a symbolic potential at the beginning of P's lifetime. But it represents the amount of potential that L is expected to get back at the end of the P's lifetime. Under this formulation, the potential of the mutable reference equals the initial potential, the wet one, of L minus the prophecy potential. We will realize the prophecy while adding a new constraint at the end of the P's lifetime. The potential associated with P must be non-negative, so it can return sufficient amount of potential to L. With prophecy potential in our approach, the analysis of mutable reference is decomposed into two independent stages. When the mutable reference is created, a prophecy potential introduced. When the reference is dropped, a constraint is generated requiring that the potential of the reference must be non-negative. In this way, we do not need to check the relation between L and P at the end of the lifetime. These two independent stages are integrated via the generated constraint. Prophecy potential therefore enables compositional reasoning about the mutable reference. To evaluate our methods, we set up an experiment. We have implemented a prototype resource analyzer named WAS, based on WAS-C compiler and a front-end plugin Karom. Here we present several cases. We support mutable reference, as mentioned above, and nested reference, and immutable reference. We support recursive function and loops. We also support different user-defined data types, not only lists, but also trees, tuples, and others. All results are expressed as linear bounds, just as our title states. Although this is not a fundamental limitation of our approach, prior AI systems have been shown to support more expressive bound forms such as polynomial, exponential, and others. To summarize, we have introduced a novel approach for resource analysis in WAS using prophecy potential. The key insight lies in effectively leveraging WAS' powerful type system to enable fine-grained resource analysis. The main highlight of our approach is the introduction of the prophecy potential for mutable reference. This allows us to suddenly check and transfer resource through mutable reference compositionally. In addition to our main contribution presented here, we also have some other significant contribution detailed in the paper. For future work, we do not support in this work for the unsafe code, closure, and nonlinear bounds. So thank you for listening to my talk. I'm happy to answer your question.
Questions? right. Well, then let me warm up the audience. So it seems like that the prophecy potentials are very much tied to the sort of borrowing system in Rust. So in what ways could this be generalized, or?
Sorry.
So,
Okay.
so to what extent is the prophecy potentials tied to essentially the borrowing mechanism in Rust versus maybe other applications where you can infer some relationship?
Let me think about. So we extend the prophecy potential for the mutable reference, of course, for the borrow and ownership system for the Rust programming language. So I'm not sure whether my answer exactly answer your question.
All right, we can discuss offline since we have another question.
Hi there. Thanks for the very nice talk. I wondered, so you mentioned some of the Rust types that you support in your approach. I wondered what would it take to extend the approach to support fancier Rust types, for example, structs that store references in their fields, etc. Do you think the approach could be extended to this language of types too?
Okay. The question is about how to extend to support more types for the Rust. We support the box type in this work, and we support the user data type, user-defined data types using a uniform template for the enum types for the ADT types. As for the types such as cell, web cells, vectors, and some other types in the standard library, they use unsafe code, interim, material. We do not support in this work, and we are considering to handle this for them, because although they are unsafe code, but they are typed as safe API, so we can give them resource annotations for the safe API, and maybe we can add some testing to generate it, the annotation automatically. We are considering to do this. Thank you.
Okay.
All right, great. Let's thank Jihao.
For the introduction. Can you guys hear me okay with the mic? No? Oh. Is it better? Okay, perfect. Okay, thank you everyone for showing up. I'm going to start by taking you back to like algorithm 201, right? Like we're starting to learn some fancy techniques for doing the design of like algorithms and doing their analysis as well. And you might have seen the randomized version of the sorting algorithm, quicksort, where we choose uniformly at random the pivot element. So if you see there's the uniform command that samples an element from the list uniformly at random. And you probably saw that in order to do the analysis of this thing, you have to solve the following recurrence relation, right? And if you do solve it, you'll be able to see that it's n log n versus n squared, which is what you can get if the list is in reverse order and you don't do this trick. But you're kind of like using your like computation intuitions about how to come up with this recurrence relation, right? Like if you have a very fancy language, how can you come up with such recurrence relations? So this is what I'm trying to answer in this talk, which is what is the semantic content of these kinds of recurrence relations? And of course, I'm not the first person who has tried solving these kinds of questions. We just had a talk about something very similar, right? But yeah, then like if you look beyond these kind of randomized algorithms, there's even more work, right? But like, so let's just focus a little bit on average cost. And I'm going to present two particular approaches that people have considered before. The first one uses this semantics that sees your program as a distribution over cost and output. And I'm using this fancy curly D here to mean the monad that assigns the set of distributions over a set. And you have this cost monoid here that counts how much cost has had. Something annoying about the semantics is that it's not really compositional in the sense that while you can compositionally compute the cost distribution, when you want to compute the expected cost of this distribution, you do this non-compositionally. So this is pretty bad. And it satisfies some weird equations that you don't want your semantics to validate. In particular, if you have the program that just loops forever, the semantics will say that this is equal to the program that first calls a very expensive function and then loops forever. And I'm pretty sure everyone here who has ever had to do like fancy Azure programming where these things actually cost money, you know for a fact that these things should not be the same, right? Like these are different programs. And our semantics should say that they're different. The other approach I want to talk about is the one based on the continuation passing style, where you interpret your program as an element of the continuation monad. So it's a function that receives as input a random variable and outputs a positive real number. And something bad about the semantics is that it is quite opaque in the sense that like you're just jumbling together the cost information with the randomness information into a single object. And if you want to obtain information about it, you have to probe it in very specific ways. So if you want to compute the, so like if you have this f here, that is an element of the continuation monad, if you evaluate it at the constant zero continuation, the semantics is designed in a way that you recover the expected cost. And if you evaluate it at this, the function that is only one at the event you care about, you recover the chance that this event will happen. But you have these weird things that happen in this semantics. But it suffers from the opposite issue, really, where it won't satisfy some equations that you do want to be satisfied, such as being able to reorder your programs, right? Like these kind of equations are very natural from a randomized algorithm point of view, where the order in which you sample things doesn't really matter, or shouldn't matter. So this kind of allows us to say what we want our semantics to actually satisfy. And one thing that we want our semantics to satisfy is this very nice separation between cost and probability, where we want to keep these things as separate as possible. We want it to be compositional, right, so that we can compute the expected cost of the whole program by computing the expected cost of its individual components. And you want it to be very, very close to actual probability theory, so that you can use theorems from probability theory to reason about your programs. If you look at the way these algorithms are usually reasoned about, it is very often that you need to use very sophisticated reasoning principles that should be, that should be easy for you to use if you want to reason about your program. And the way we have solved this is by using this expected cost monad, where we just pair the expected cost given by a positive real number with the probability distribution on the output space. And something that I think is very, very nice about this monad is that it has a very intuitive meaning in terms of cost semantics, or rather average cost semantics. So you have the unit, which is like the operation that just outputs a value, and it should have no cost component, and it should have no randomness to it. So it just outputs 0 and the point mass distribution at the input. And if you want to sequentially compose your programs, this is how you do it. You imagine that you have a function from A that outputs the average cost of running it and the output distribution, and you want to see how to compose it with another effectful computation. And I'm not going to show the random part of this thing, because like it is not that interesting, but the cost one is quite interesting. And it just follows the idea that the cost of sequentially composing programs should be just the sum of running the input plus the sum of running the continuation given the input. But now we make things random a little bit, right? So we add the expected cost of the input. So you have this R here, which is the average cost of the input, plus the cost of the continuation, but it's average. So you have here, it's the cost, the average cost of the continuation given input A, and then you average out by the input distribution. And just to show this very simple protocol, imagine that we have this thing where we have an infinite pile of coins, and at each round, we first pick a coin, flip it. If it's tails, it's over, it stops. If it's heads, we put this coin in our pocket and then get another coin. And then we do this until until it's tails. So this is the geometric distribution, and it can be represented as this very simple functional recursive program, where let's just assume that we have an operation flip that with bias B flips a coin, and with chance B and with chance 1 minus B, right, of heads and tails. And if it's true, you add 1 to your counter, and you recursively call your program. If it's false, you just output 0. If we are to analyze this algorithm using the cost semantics we showed before, you see that you have to do a lot of very annoying algebra. So because it is a function that uses recursion, its semantics has to be some kind of fixed point. And so let's just assume that we have solved the fixed point equation, and it has given us this following distribution that is just a geometric distribution. If we are to compute the expected cost of it, we have to compute this infinite sum. And I don't know if you guys know, but this can be very annoying. And and the annoying thing is that you lost the recursive structure of the program when you map it into this format, and you have to rediscover the recursive structure of your program by doing some algebra. So you see here, after doing some algebra, you're rediscovering the original expression, and now you can solve the semantics. Sorry, the cost. On the other hand, if we do the expected cost semantics, the semantics itself, the fixed point equation you have to solve, is already taking care of the recursive structure of the program for you. So the semantics is just this equation, which is just very easy to solve. Like, it's just a first order equation. So like, this is just one more semantics, right? Like, so you might think, okay, we already had semantics before, so why do we care about this new one? And something that I think is quite nice about this kind of work is that you can formally relate these semantics with other semantics, right? Like with the semantics I showed before. And I do this by proving the following theorem, which says that the expected cost of the cost semantics is upper bounded by the expected cost semantics. And the reason why it's not an equality is because of those weird equations I showed before. So if you restrict to the terminating fragment of your language, you do recover equality. And it gives you the same cost analysis as the continuation passing style semantics. And something else that we can say in this case is that if you look at the concrete semantics we have used, you can actually prove something even stronger, which is that our expected cost semantics in the category of quasi-Borel spaces with order, the expected cost monad is exactly the affine fragment of the continuation monad. And of course, I mean affine in the algebraic sense, not in the PL sense, though they are very much related. But it just means that the continuation can be written as a sum of a constant plus a linear operator. So like the idea being that it's the cost plus the probabilistic aspect of the semantics. Yeah. And if you go on the paper, there's a bunch of other stuff we have done. I just want to focus on the first two, which showcases why we need to use these fancy quasi-Borel spaces, because we have high-order functions, we have continuous distributions, and we have recursion. So we need sophisticated semantic domains. And just a parting thought is that even though the semantics I've used is quite concrete, the idea of this expected cost monad is very general. So if you have other kinds of applications where you want to reason about average cost of your program, but you have a different semantic domain, you'll most likely be able to adapt the monad to your application. Yeah, this is all I have to say today. Thank you.
Questions?
Hi, the talk was great. Thanks for that.
Thank you.
I was wondering if in the process of applying these semantics to get expected cost for some of the programs, that you run into any interesting inference problems where the semantic led to some algebraic form that you needed to solve using probabilistic inference.
Yeah, for sure. Like, even though I showed the expression you get, like there is some, there's one simplification here that you have to do, which is to use the fact that your program terminates with probability 1. So like these are the kinds of things you have to think about when doing the analysis.
Right.
And kind of show it, yeah.
Okay. I would be happy to talk offline more about
Yeah, for sure.
Thank you.
Morning, everyone. So IncIDFA is an efficient and generic algorithm for incrementalization of any IDFA or iterative data flow analysis. An IDFA is an important class of static analysis where we propagate information across the edges of the control flow graph in order to obtain some meaningful information about the program, such as reaching definitions. Sorry, I have no idea what's happening. The adapter is fine. Can I please get your laptop? I'll just switch the laptop, sorry for that. Actually, a laptop would be better, I guess. Okay, let's try this again. Yeah, hi, sorry for that. Okay, so during compilation of a program, the program may undergo various optimizing transformations. As a result of these program transformations, the data flow solutions or the analysis results may be rendered stale. That is, they may not conform to the modified state of the program. There are two options for stabilizations in this scenario. One is when we completely invalidate and recompute the solution from scratch. Second, when we incrementally update the solution, the old solution, with the help of the set of program changes that we have in our hands. The first approach is precise and easy to automate, but it is clearly very inefficient because most of the times these program changes might impact only a small part of the data flow solution. The second approach, which is incremental update, poses an important question, which is what is the generic incrementalization approach or algorithm that can apply for any new arbitrary data flow problem? And the goal is to have a precise, efficient, and fully automated scheme. To recap, what exactly is an IDFA? So for each control flow graph node n, we maintain two flow maps, inflow map and outflow map. Inflow map is nothing but merge of incoming information from the predecessor nodes, whereas outflow map is the impact of processing node n given this inflow map. So these are the two equations which we use to denote the in and outflow maps, the meet operator for inflow map and transfer function applied on inflow map to obtain the outflow map. In a standard worklist space algorithm, we obtain the maximum fixed point solution by applying these data flow equations until we reach a fixed point, that is until there is no change in the flow maps of the nodes. Here's an example constant propagation analysis application where we have a program snippet and its control flow graph. The target here is to identify what variables may have constant values at what program points. We model three values here, top, integer, and bottom. Top corresponds to least informative in this representation. Bottom is the most conservative value. So this is the fixed point solution for the application of this analysis, where we can see that at node n4, y is equals to ident y. We do not know what exactly is the definition of this function ident. Hence, y will be set to bottom at this program point, and hence it will bottom in the loop as well as outside the loop. Now let us say after finding the fixed point, the compiler identifies that ident is actually an identity function. So this is same as y is equals to y. Clearly this is dead code and we would want to remove this. Once we remove this, we see that now we have only one write to y, which is y is equals to 2 in the first node and not. However, still at n6, we see y as bottom. So this explains why do we require stabilization, because here, even though y should be 2, it is bottom. As a result, I cannot replace n6 with print 2, which is something that is very obvious to us. So in the literature, there have been multiple incrementalization approaches. Let's assume seed nodes is a set of nodes whose immediate predecessors have changed as a result of the program changes. In the restarting iterations algorithm, we populate the worklist with the seed nodes and apply the standard worklist-based algorithm from scratch. There is an issue, however. In the restarting iterations algorithm, we may read from the stale values of our predecessors. As a result, what we may generate could be the imprecise solution. A simple mechanism to address that is to have a naive two-step algorithm, where in the first step, which is the initialization step, we will reset all the flow maps which are reachable from the seed nodes. And after that, we will just apply the restarting iterations again to come up with the fixed point solution. So init restart will guarantee that what we obtain is the maximum fixed point solution. However, it can be inefficient, especially since, let's say, if the seed node is at the beginning of the program, then it may end up like resetting the complete program. So the solution is IncIDFA, which is a precise and efficient incrementalization algorithm. We attain precision using a similar two-step approach of initialization and stabilization. And we attain efficiency through 4 key optimizations. The first one is we stabilize one SCC, or a strongly connected component, at a time. And we process other successor SCCs only if there is a requirement to do so. To optimize the initialization step, we say that instead of resetting the flow map blindly for all the nodes in the SCC, let us just ignore the stale flow maps for the time being. And we do that while processing the new flow maps for any node. In the second optimization of initialization, we say that instead of starting with the least informative value for any of the nodes, what we should do is unconditionally propagate the information from the entry point of an SCC up until the seed nodes so that we have some meaningful information to start with. And in the optimization of the stabilization step, we apply the iterative algorithm on only a subset of the nodes, not all the nodes, unlike the previous approaches. So let's look at the first two optimizations here. So we established in the paper that all the imprecision originates within the cycles of the control flow graph. And all the cycles are present in the maximal SCCs of the graph. Hence, if we take one maximal SCC at a time, we should be still able to guarantee precision. Now let's look at this abstract control flow graph. Let's assume that this red colored node S is a seed node. If we apply both the steps, initialization and optimization within S1, that is S, E, and A, then after that, let's assume that outflow map of A doesn't change. In that case, the incoming information to S2 is not changing, and hence we can safely declare that we need not process S2 or any of the SCCs which are beyond S2. So that can lead to a lot of savings. In the second optimization, so as part of this optimization, one of two of the initialization step, instead of resetting all the flow maps of the nodes in the SCC, we maintain two special set of nodes. First one is about the safe nodes. So a safe node is a node whose flow maps do not contain any imprecise values. So intuitively, when we are performing the processing of different SCCs in the topological sort order on the SDG, we know that all the prior SCCs are safe. And similarly, any node whose inflow map or outflow map was computed with only the safe nodes will also be safe. Then when we talk about under approximated set, it's a set of those nodes for which during the calculation of its inflow map, at least one predecessor was ignored because maybe it potentially had some unsafe value. We process any node at most once, and when the work list is empty, we declare that all the nodes in the SCC are safe. So here's a very small example to understand this. Let's focus on the SCC S1. Let N1 be the seed node. When we start with N1, safe nodes are empty, under approximated set is empty. While processing N1, we will ignore N1000 because it is not a safe node. So we potentially, it could be unsafe, so we ignore that. Since we are ignoring that, N1 will be added to under approximated set. Since we have processed N1, now it is a safe node. And let's assume that out of N1 changes, so we will add N2 to the work list. While processing N2, we can notice that N0 belongs to previous SCC, N1 is already safe, hence we will consider both of their outs to obtain the new in. Let us say the out of N2 doesn't change, so the work list will now be empty. N1 and N2 both are safe nodes, and N1 is under approximated. Now since the work list is empty, we can declare that the initialization step has terminated, and all the nodes in S1 are safe. Now do we see any savings here? One thing, we have 1000 nodes in this particular SCC. However, we were able to achieve the initialization steps completion by just processing 2 nodes. So without this optimization, we would have to process 1000 nodes instead of just 2 nodes. And now the guarantee, the big claim that we make is that even though we have not touched these 998 nodes, their values are still safe. So the question is, where is the proof? It's in the paper. So in the paper, we have provided formal definitions of the flow graphs, data flow analysis, and data flow solution. And we have provided operational semantics on an abstract data flow analysis. We have given proofs of its termination, soundness, and precision. We have implemented IncIDFA in the IMOP compiler framework, as well as its 10 instantiations, such as reaching definitions, liveness, points to log set analysis, and so on. We have performed evaluations on 24 benchmark programs across 4 benchmark suites, and we have performed evaluations across the dimensions, across the dimensions of IDFA stabilization time, total compilation time, as well as we have verified its empirical correctness. So in this graph, we are showing the stabilization time speed up for IncIDFA and the proposed approach IncIDFA, and init restart, which is the naive 2-step approach, as compared to CompIDFA, which is full recomputation, like exhaustive reanalysis of the program. So we can see that the gains depend mainly upon the reduction in the fraction of nodes that are processed during the incremental update. And we can notice that IncIDFA consistently outperforms CompIDFA as well as init restart because we notice that Inc IDFA will process significantly lesser number of nodes. For example, for case of EP, Inc IDFA processed only 34.4% of nodes as compared to Comp IDFA, resulting to 11x improvement. Similarly, as compared to init restart, we see 4x improvement in EP because Inc IDFA Inc IDFA processed only 27.8% of nodes as compared to what were processed in init restart. So to summarize, Inc IDFA is a novel, precise, and efficient algorithm for incrementalization of any arbitrary IDFAs, and we affirm its generality, practicality, and efficiency with the help of the formal treatment of the algorithm, its implementation in a real-world compiler framework, as well as its empirical benefits. So thank you for listening to the talk, and I would love to take the questions now.
Questions?
Yes. Thanks for the question. So the example was interprocedural, but the evaluation graphs that we have seen are for interprocedural, context-insensitive, inter-thread analysis, because this is for OpenMP programs. So it's not just interprocedural, but also inter-thread analysis. So, I mean, I hope that it establishes the complexity. Sorry? So when we have ran the experiments, we did not synthetically generated any program changes or stabilization triggers. Instead, we actually took a real-world set of optimizations called as parallel, which is a set of optimizations which are required to remove extra barriers in OpenMP programs. So when we are running this real-world set of optimizations, we took the organic set of changes that were generated as a result of this optimization, as well as the number of times the program changes or rather stabilizations were triggered. So these were all organically taken from the BarLM optimization pass, which is already a real-world pass in IMO. So, yeah, thanks. Yeah. Thank you. So we have cited most of these papers in our paper. The only reason we do not make the big claim that it is wide enough to capture all the abstract domains is because our proofs are limited. So like our proofs are applicable only for iterative data flow analysis, and that's the reason we have confined the claims to that level. But intuitively, we also believe that it can be extended to handle wider set of domains. Yeah.
Why does it not do every single thing? Like what optimization is missing? The first one is definitely there.
Yeah.
Strongly connect components separately.
Yes.
There. The second one, I'm not 100% sure. I think it's there. So can you give me an answer on what's missing?
Actually, second one is not there. So from what we have checked, we do not actually maintain the set of nodes as safe nodes and under approximated nodes. So that's a formulation which is not there in the papers that we have looked at. And we also have some other optimizations that I couldn't explain here because of lack of time. So like for example, one of them is that we make sure that when we talk about a certain SCC and do a processing for a seed node, we do not start with the least informative value, because that's the most precise, the most generalized version of a precise answer that we can get. So we start we have a two-phase approach there, where we start propagating information from the entry nodes till the seed nodes. So these are the kind of optimizations that are not there in any of the DSL or data log based data flow analysis like INK and others. Okay, thank you. Thank you.
working? Okay. Hello everyone, I'm Flavio Ascari, and I would like to present the work I did together with Roberto Boni, Roberta Gori, and Francesco Logozzo. In title, Revealing Sources of Memory Errors via Backward Analysis. So we make two main contributions in our paper. One is more conceptual, is the first one, that is sufficient incorrectness logic, that is a proof system tailored for backward inference of the sources of errors. And the second one, that is the more technical contribution, is separation sufficient incorrectness logic, that is a version of sufficient incorrectness logic mixed with separation logic to handle memory allocations and programs with heaps. So the first contribution, sufficient incorrectness logic, there are like a lot of program logics in the literature that are good at, very good at some specific tasks, but we started with this question, that is identifying initial states that are useful for debugging. So consider this simple program where y is some variable that comes from the, let's say, the environment somewhere in the program before that. Here we get some x from the user, so an input. And depending on some condition on x and y, we set z to 42, that is the error. So the condition we are aiming for is to understand that, let's say, a precondition responsible for the error is that y is odd. Of course, we would also like to have something on x, but we can't because x is an input of the user. So the best we can say is a condition on y, and we want to understand that if y is odd, then we always have like a possible execution where the user inputs an even number that will lead to the error. So to this goal, we started considering some known program logics from the literature. We started with OR logic, very well known, and incorrectness logic. That is a logic for under approximation aimed at finding bugs, so it seemed a good fit. But for both of them, we found that they have some issues, because you can see here that if we want to identify the errors z equal 42, we get some preconditions that are not really what we're looking for, because one is false and the other is true. There is sort of an indication of the error in the post-condition of incorrectness logic, that odd of y appears there, but is not such a general thing that we can rely on that. So since our goal was starting from the error, so this z equal 42 in the post condition, and we wanted to find the corresponding precondition, we thought, okay, maybe the issue is that both OR logic and incorrectness logic are based on the forward semantics, so they kind of follow the program forward where we want to go in a backward direction. So we considered instead a backward program logic in the literature that is necessary preconditions, and it has some better properties because of its backward nature, but it still doesn't capture the property we're looking for, because for technical reasons, for necessary condition, we want to consider the set of good states, so z different than 42, but still you can see that the precondition is true, so it's not highlighting the thing that we are interested in. And so, as you probably may guess from the schema on the right, what we turned our attention to was the backward under approximation condition. And as you can see here, the bottom line, when we start from z equal 42, we are guaranteed to find the fact that y is odd, or let's say a subset of it. And so this backward under approximation condition was exactly the thing that we were looking for this specific task of identifying initial states for debugging. Also, you see that I'm calling it backward under approximation condition, but on the slide you see the SIL name. The point is that the backward under approximation condition is not our contribution, but sufficient incorrectness logic are. I will get back to this point in the next slide. So for now, let me just try to give you some more evidence of the fact that this condition is useful. So the idea is that, why are we interested in this condition? I think the example already showed the idea, but the point is that in a SIL triple, if all states in the postcondition queue are errors, then from any state in the precondition P, there begins an execution. That there may be executions leading to good states if, for instance, the user inputs a particular value, but there is also a value that the user can input that will lead for sure to an error in Q. And so the precondition found by SIL is useful to pair together with Q to give input states that are evidence for this error that can be used for starting the debugging process. Another example of usefulness is the concept of manifest errors. The manifest errors were introduced by Lee et al. in the concept of incorrectness logic. They were manifest errors are errors that happens regardless of the context, and they were tested experimentally in the sense that they reported errors to the programmers, and the programmers usually fixed the manifest errors, while they usually didn't fix errors that were not manifest. So these are actually a practically relevant concept. And in the context of incorrectness logic, you need to check separately after finding the error if it is manifest or not. But with sufficient incorrectness logic, you can prove this already within the logic itself, just checking that this triple is valid where the precondition is true. So, as I said, the condition of backward under approximation, that is the validity condition of seal triples, was already proposed in the literature. Our new contribution in this sense is the proof system. What we gave was the first proof system for this backward under approximation condition that is tailored for a backward inference. So starting from any post-condition queue, the proof system guides you towards the initial states corresponding to that post-condition, and also the comparison that I showed you very briefly before with other logics. As I said, this is the first contribution of our paper, that is the more conceptual one, but we also have the more technical part, that is the separation seal. That is, as you may expect from the name, a combination of separation logic and sufficient incorrectness logic. And I mean, there are a lot of technical details, and you can find all of them in the paper, but here I will just go through an example plus some remarks later. So consider this program. In this program, you have V is a standard C++ standard vector library. And what we're doing here is we use X to take a reference to the underlying buffer to the vector. Then we do a pushback, so we add an element to the vector V, and then we dereference this X reference that we got before. But the issue is that the pushback may reallocate the underlying buffer to the vector if there is not room to account for the new element. And if this happens, then the pointer X becomes invalid. As you can see, in separation seal, if in separation seal we want to capture this error, we start from the post condition that says exactly that X is deallocated, that is the error that we have, and separately true, and that means we don't care about the rest of the heap, because knowing the fact that X is deallocated is the only thing we care for the description of the error. And then using the proof system, we go backward through the program and we find the precondition. Basically, this first part here says that V is just a valid vector. And separately true, again, means that we don't care about what else is in the heap. We only care that V is a valid vector. And the very strong guarantee that we get from this triple is that from any state satisfying the precondition, so from any state where V is a valid vector and whatever is the rest of the heap, then there is an execution that reaches the error. That is exactly the case when the pushback decides to reallocate the buffer. If we, for instance, compare this with the incorrectness separation logic triple, we see that because of different goals, the incorrectness separation logic triples is a lot more precise on the post condition. It says that there is the error where X is deallocated, but it also has to specify a lot more about the shape of the heap there. And also the precondition, you again see the error, but this is not always the case because separation logic allows for weakening of the precondition or strengthening of the post. That is basically the same thing. And so in principle, you may find here more states than the ones that actually lead to the error. So in principle, a tool based only on incorrectness separation logic may have more states in the precondition that do not lead to the error. So just a bit of technicalities, but I think that I really want to mention about about separation seal is this theorem. So one very important thing that I forgot to mention is that P and Q in separation seal are assertions. So they are a syntactic object in assertions in a certain language, so something that you can manipulate programmatically. And the theorem says that for any syntactic assertion Q and any atomic command C, atomic commands are basic statements such as assignments, dereferences, allocation, and so on. Then there is another syntactic assertion P that is exactly the backward semantics, so let's say the strongest seal precondition for this assertion Q. So the assertion P is a syntactic one. And we can prove this triple. And the proof is very interesting because it's not just there exists one, but it gives you an algorithm to compute exactly this precondition, this assertion P. So on the one hand, the theorem is the basis of our relative completeness result, where we extend this from atomic commands to any kind of command by composing them. But it's also, the proof is a basic of, let's say, more practical applications, where because we implemented this algorithm in a proof of concept implementation, it was part of a student project, and this validates our intuition that we can do backward inference using separation seal. So, to conclude, there are in the literature many approaches to program correctness and incorrectness. We sorted and compared some of them, and we designed the sufficient incorrectness logic proof system as a sound and complete system, proof system for backward inference. And we provided an automated, or at least automatable, proof system for backward inference in the case of memory errors based on separation logic. As future works, we would like to extend the schema by including other logics, so to compare this more complex logic with the basic one that I showed you. And also, one future work that we actually did was the idea to follow incorrectness logic derivation backwards with SIL, and this is a work that I'm happy to say that has been conditionally accepted at POPL 26. That's all from me. Thank you for your attention, and please feel free to ask any question.
Questions? All right. So super interesting talk. Thanks for it. So I guess I got a little bit sort of lost in terms of exactly the precision difference that you were talking about between the incorrectness separation logic and yours.
Okay, so very briefly, what can happen in general is that while you go forward with analysis in incorrectness separation logic, you may the postcondition may grow bigger because of different code paths that leads to disjuncts. And if you reach some limit of disjunct, you may have too many to keep track of programmatically, so you want to drop some of them. And if you do, like some of the states in the precondition that led to those disjuncts in the post now don't lead to any error that you have still left in the post because you dropped the only disjunct that they were reaching. This is the kind of issue that you incur into if you do an incorrectness logic kind of analysis, let's say in a more practical setting. Instead, separation seal does the opposite. It guarantees that all states in the pre will reach some states in the post, but of course, while going backward, you may need to drop some disjuncts, so some states in the post may end up not being reachable. So okay. You have this kind of duality in where you have the imprecision.
Right. Oh, super interesting. I'd love to talk further. You want to set up? Yeah.
Yeah.
Okay.
Can I ask a question? Okay. I'm sorry, I'm new to the field, so could you briefly explain?
Hello everyone, I'm Chemo from Nanjing University. The authors of this paper cannot give the talk today, so I will give the presentation instead. I don't participate in this work, so if you have any very detailed technical questions, please contact me offline and I will pass them to the authors. The title of this talk is Two Approaches to Fast Particle Force End for Static Analysis. Let's start with the background. Program analysis is a material field with applications like security analysis, compiler optimization, and program understanding. All of these are powered by the static analysis framework. So what does a framework need to do? In a general workflow for program analysis, we usually go through several stages. After input program, first, translating source code into an intermediate representation. Second, running fundamental analysis, such as code graph construction. Third, running client analysis, such as vulnerability detection or test analysis. And finally, getting results such as vulnerability reports. Almost all analysis frameworks, including this classic static analysis framework for Java, need to support both IR front-end and fundamental analysis. In other words, the IR front-end is indispensable. So why do we need a new front-end? The efficiency matters. In many cases, researchers want to run analysis quickly and get results fast. A faster front-end directly speeds up the entire analysis workflow. However, the existing works are still too slow. Existing front-ends are even slower than the subsequent fundamental analysis. Like RTA take only 49 seconds on a benchmark, where current front-ends take longer just to translate IR, but will only take 4 seconds. We built a new and effective front-end and compared to the existing works, our front-end is on average 10 times faster and up to 600 times faster in some cases. We achieved this through 2 new approaches, and I will explain shortly. Our implementation is based on a tile framework, and we provide an open source artifact. Now let me introduce our design. A typical front-end goes through several stages, like crossword construction, class hierarchy construction, the three address code, translation, and type inference. On this, the last 2 steps are the most complex and time-consuming. First, in the 3 address code translation step, we need to translate Java bytecode into the 3 address code. This step has 2 key challenges. The first is the bytecode data flow is step-based. For example, the statement a equal 1 means slice, push the constant 1 onto the stack, and then pop it from the stack to store it in the source 0, corresponding to variable a. And the second is different variables may share the same variable slots. For example, when computing the variable c, it might reuse the same slots like variable a used. This makes its data flow is quite different from the typical data flow. We can't directly get the value of variable c from the bytecode. We have to follow the stack to check the data flow. For this problem, we propose our first approach, pattern-aware 3 address code translation. Specifically, the bytecode defines 2 defined use patterns, A and B. For pattern A, the right edges in the figure represent the stack defined use. For example, in the second line, A equal P, it corresponds to the first right edge on the right. This line compiles into 2 bytecode instructions, I0 and I1, where 0 and 1 represent the slots storing variable P and A. This instruction means that the value is loaded from source 0 and push it onto the stack, and then pop from the stack to store into the source 1. This is the stack defined use. For pattern B, the blue edges in the figure represent local defined use. For example, before in the first line, A equal A81, source 1 already stores the value of variable A. We then load it from the source 1. And when you use in the first line, this is a local defined use. If you are still not very clear, we can just focus on the structure of the right and blue edges. For pattern A, there are no back edges, which means the definition of a variable always before its use. In contrast, pattern B may has the back edges. In this case, loop can make a variable to be used before it's defined. So what problem does this cause? Without the back edges, we can generate 3AC in one pass using reverse post-order traversal. It's simple and fast. So in our approach, we use different methods to handle the different different pattern. For pattern A, without the back edges, we can use one pass to generate 3AC. It's simple and fast. For pattern B, it may have the back edges. We handle this by the inserting 5 nodes to translate it into the SSA form, which removes the back edges. We use the standard SSA algorithm. In this process, we only need to handle about 20% bytecode instruction, so it's very fast. After removing these back edges, we can use the one pass again. In summary, our approach is to handle simple pattern A using a fast and a simple method A, and handle complex pattern B using a complex method. However, existing works use only one complex method C, a single method, to handle all patterns, include the simple pattern A and the complex pattern B. This makes they have the redundant computations, which slows down their translation. Now we have translated the bytecode into the 3-address code. However, this 3-address code doesn't have the type information. For each variable, we don't know its type. It's marked with a question. Because the bytecode is untapped, naturally the resulting 3AC is untapped. But the type information is important for analysis. Missing the type information, for example, it may cannot resolve the method calls precisely. So we need the type information. So we need the type inference to get the type information. In general, type inference is viewed as a constraint solving task. For example, for this case, in a 3-address code, the statement A equal new hash map means that the hash map is a subtype of A. Similarly, tree map is also a subtype of A. For the statement B equal A, we know that the A is a subtype of B. For invoke statement like B point map points clear, we can infer that B is a subtype of map. Based on these constraints, we can build a type constraint graph. And we can also get the program's type hierarchy in advance. So how does existing sorter algorithm handle this? They start from the root nodes and follow the arrows. Since the types of the hash map and the tree map nodes are already known, they don't need to handle. When handling variable A, since A is a parent type of its predecessors, they need to find the least common ancestor, the LCA of those predecessors in the type hierarchy. So the type of variable A may be the map, serializable, or clonable. For variable B, because it's the parent type of variable A, its type may also is the same 3 types. When they handle the last node, the variable A and B each have the 3 types. However, according to the constraints, B is a subtype of map, and variable A is a subtype of variable B. So the sorter algorithm finally filters out the redundant elements and gets the variable A and B is a type map. During the traversal, many redundant elements are computed, which slows down their process. For this problem, we propose our second approach, pruning-based type inference to handle it. So what's different with the sorter algorithm? When we handle the variable A to get its results, we use the constraint to filter the results early. And during the traversal, we don't have many redundant elements, which reduce the redundant computation. It makes our approach faster than the sorter algorithm. Even if pruning still multiple LCAs, we simply choose one non-deterministically. Why is reasonable? In our paper, theorems 4.1 to 4.4, we formally prove that most programs satisfy a property ensuring our algorithm is correct. Due to the time limits, I will not go into detail, and the experiments show that our algorithm produce no incorrect results. So how does our force end perform in practice? We built a large and diverse benchmark and compare our force end with the most popular and well-established static analysis framework, SPLASH'25 and SPLASH'25. For efficiency, our force end significantly outperforms all others, both in three address code, translation, and in type inference speed. Specifically, our force end is on average 10 times faster and up to 600 times faster. Reliable is also important for force end. It affects the backend analysis. In terms of reliability, we also perform the best, successfully processing all input bytecode methods. Finally, our force end is implemented in tile framework and will be released soon. If you are looking for a faster and more reliable force end for Java, welcome to learn and use tile. In the upper right is the QR code of the tile website. If you have any detailed technical questions for our force end, you can contact me offline and I will pass them to the authors. Thank you. That's all.
Take some questions.
Thanks for the talk. First, my question is that is your 3 address code in the SSA form?
Yes.
What's the difference between your algorithm and the memory to SSA algorithm and RVM? Do you know memory to SSA?
Oh, I don't know this mean.
Oh, I see. So that's an algorithm that if you store variable to the local stack or local memory, and then like every time you load from the local memory is a use, and then that's a defined use. Then you can use the standard SSA construction algorithm to construct the SSA form. Oh, okay. Maybe we can discuss later. Yeah.
Okay. Thank you.
Just I have 2 questions for you. So one of them is when it comes to the type reference, how do you determine the dynamic generated object? Yeah.
Pardon?
Dynamic generated. Yeah.
Dynamic generated.
Sometimes through the lack of reflection.
Oh, I don't know this detail because we generate the constraints advance our analysis.
Okay. Another question is about because the most Java applications is like large scale applications. So how do you transfer to your optimize IR to bytecode of the large scale applications? So something like a Spring we used in realistic world. Because I'm considering how to leveraging. If we try to leverage the framework to optimize, you have to a way or to transfer back to the Java bytecode. Yeah.
Oh no, we can't to transfer it to back the bytecode for IR.
Okay. So because I'm considering because like when it comes to the suit, you can compile convert original IR to get back to the bytecode.
We don't provide
and
it.
Get that from there to for optimization. Yeah. Okay. Cool.
Let's thank Mei Long. Thanks for being at the Analysis 1 session. So lunchtime.
right. Good afternoon. One thing they forgot to mention in the proceedings is that this is the most interesting session. Okay? It's a secret, don't tell anyone. And this will be made interesting by 6 speakers. The first speaker is Mingyuan Liu from Fudan University, and he'll be talking about diffing Android applications. Mingyuan.
Introduction. My name is Mingyuan Luo from Fudan University. Today I'm here to present APK Differ, a novel tool for accurate and scalable cross-version diffing analysis for Android applications. In a nutshell, APK Differ takes 2 different versions of the same application and precisely identifies methods which have been added, removed, modified, or remain unchanged. For example, method A here is aligned with A prime, which is modified, and method B has no alignment since it is removed, and method D is aligned with method D, which remains unchanged. Method alignment can ease the auditing of application updates, since it helps us focus on the exact change introduced by the application updates. And it also helps with the reverse engineering, since we can easily migrate the knowledge of the old version to the new one. In fact, method alignment is a graph matching problem. We can represent each application version as a call graph, where methods are nodes and calls are edges. The problem then becomes finding the correct correspondence of the graph nodes. However, this is where we run into our first challenge, the scalability. Graph matching is well known as an NP-hard problem, which means that its complexity explodes as the graph size increases. Additionally, modern Android applications are massive, containing tens of thousands of methods, which means that trying to match these large graphs is computationally infeasible. Our solution to this scalability problem is to divide the whole call graph into small subgraphs, which we call it functionality-driven graph composition. Here, we leverage the event-driven design of Android applications. In Android, a user clicks a button, the system sends a notification, or the component lifecycle state changes are all events. We treat the code that handles these events as distinct functionality units. And then APK Differ partitions the whole graph into smaller subgraphs, and each of the subgraph is corresponding to one of these functionality units. For example, we can separate all methods starting from the callback of the next button click to form a subgraph, which is marked as green in this figure. To identify the callbacks of these events, we manually construct a whitelist of framework classes where the callback interfaces are defined, and then we identify application callbacks that override these frame callbacks. Once we have these smaller subgraphs, we need to match them across versions. We do this by finding the unique event ID of each subgraph, which tends to be stable across versions. For example, the subgraph marked with green has a unique ID next button, and in the newer version, there is a subgraph which has the same unique ID next button. Then we can match them by matching this unique ID. Here is a concrete example that how we use the program analysis to locate the event ID. Briefly, we use data flow analysis to identify the GUI element of the on-click callback here. Now for our second challenge, accuracy. Existing work often make a trade-off. For example, linear assignment aligns the most similar nodes according to their code similarity, mainly uses node similarity but ignore the edge similarity. And another example is neighbor search. It sets up an initial set of aligned methods using simple heuristics such as containing the same string literals, and iteratively adds the neighbors of the aligned methods to this set. However, it focuses on the edge similarity but ignores the node similarity. Additionally, none of these existing works effectively handle end-to-end alignment, which occurs when the developer refactors the code. These figures show the cases of end-to-end alignment. Specifically, figure B shows a 1-to-2 alignment. In the old version, A calls method B twice and method C, but in the newer version, A calls method D and method C. However, D calls B twice, so they do the same thing as method A in the old version. They should be aligned. And figure D shows an example of end-to-end alignment. In the old version, method A and method D calls a sequence of methods, namely B, B, C, C here. And in the newer version, method A and method E calls the same sequence B, B, C, C. So A and D should be aligned with A and D here, since they do the same thing. And to our best knowledge, existing works literally ignore the end-to-end alignment. To tackle the accuracy, we introduce a three-stage process. The first stage is anchoring. We start by running a fast but basic alignment using linear assignment. This stage only considers the node similarity and possibly produces significant errors. And this stage can be formally modeled as an optimization problem. Specifically, given a matrix P where Pij equals to 1 means that method I aligns with method J. We search for all possible values of this matrix to find one that maximizes the sum of node similarities, which we denote the result as P star anchor. Second stage is refining. This is the crucial step. Here we introduce edge similarity to correct the anchoring result. The edge similarity here is defined as the percentage of correct aligned neighbors. This process can also be modeled as an optimization problem. We are still searching for an alignment matrix to maximize the sum of similarity. However, the difference here is that we use a new similarity matrix, SimFusion, which adds the edge similarity to its calculation. This figure shows an example. It notices that method B is matched with method C prime, but their neighbors don't match up well. The neighbors here are method A and method H in the old version, and A prime and D prime in the newer version. Here, method A is matched with A prime, which is correct. However, method H is not matched with D prime, which is unexpected. So the refining stage can confirm that B should not be aligned with C prime, and in consequence, it will search for better fit like B prime. Finally, stage is expanding. In this stage, we are looking for those end-to-end cases. We do this by checking the neighbors of aligned methods to see if merging a smaller unaligned method back into its caller would create a much better match. For example, in this figure, we check the F prime, which is a colleague of the E prime. We merge F prime back into E prime as one single node, and then we use a new similarity matrix designed for two method sets to evaluate the similarity. And this helps us find a 1-to-2 alignment here. And here is the evaluation part. We evaluate the APK differ against four baselines on our benchmark, namely greedy search, linear assignment, and neighbor search, and PE-joid. As the result shows, APK differ significantly outperforms all others in both precision and recall. Specifically, it improves about 4% to 34.5% accuracy and 16% to 64% recall. In terms of the time cost, APK differ spends about 24% of time on graph decomposition and about 57% on the method alignment. And in average, APK differ needs 9 minutes to analyze one application. Although it is not the fastest tool, it has a reasonable time cost and the best accuracy. To prove its real-world utility, we use it to evaluate the evolution of privacy collection behaviors. Specifically, we evaluate 100 applications scattered from the Google Play Store, and the conclusion shows that many privacy collection behavior is added and many is deleted every quarter of a year. And we further investigate the causes of the privacy collection behavior, and we found that 70% are due to the functionality updates and some are due to the library integration. Most importantly, we can dive into the code. We found cases where updates introduce new privacy threats. For example, we recorder added the feature that slightly leaks the device ID to web pages. And another example is the form master. In an update, it started tracking for GPS status and leaking location data from a shared component. And all of these cases are subtle but dangerous changes that tools like APK differ are designed to uncover. And finally, APK differ is fully open sourced. You can scan the QR code to get its artifacts, including source code and datasets. And if you have any questions on how to use it, please feel free to contact us through email. And thank you for listening.
Thank you for the excellent talk. Questions?
That's very nice. When you do the precision and recall, how do you know what the ground truth is?
The ground truth is since we can intercept the compilation process of each APK, and so in this process we can just mark the ground truth by some many worker and instrumentations.
When you do this matching of two different apps, so when you have two different versions, I believe most of the functions remain the same, isn't it?
Yes.
In such a case, if most of it is the same, if I take a very simple naive scheme that just says the function is exactly the same, they are matching, how much percentage would that be?
Oh, we actually we do not calculate the percentage of the functions that totally remains unchanged. We just evaluate the accuracy, like precision and recall here.
Okay. The second question, you had a slide on expanding, right?
Yes.
So there, do you take into consideration that a functions may be called F1 first, then F2, or F2 followed by F1? Do you maintain dependencies? Do you have to take care of dependencies as well?
Dependence, you mean that in such as
yeah, let's say
this case?
Yeah, let's say calling B1 first and then B2.
Yes.
And I change it to B2 followed by B1. Is it same or it's different?
You mean that if we change the sequence of this BBCC method? Or
right.
Yeah. We are this sequence sensitive. We can identify they cause the same sequence here.
Oh, you are sensitive to that?
Yeah.
Okay, cool. Thank you. Any other questions? No? Let's thank the speaker again.
Yes.
The second talk will be given by Tianchi Li on combining formal and informal information. Tianchi.
Okay, so thank you for your introduction. Good afternoon, everyone. I'm Tianchi Li from Peking University, and today I'm going to present my work on how to combine formal and informal information in Bayesian program analysis via soft evidence. And this is a joint work with my advisor, Xin Zhang. So let's begin with the motivation. While conventional program analysis have developed for decades, they rely on the formal semantics of a program to reason about its behavior. However, programs also contain a lot of informal information that this analysis typically ignore. This kind of information includes the names of variables and methods, and string constants, and even comments. It can provide valuable hints that developers intuitively use to understand the code. For instance, variables which have similar names are more likely to alias with each other, and a code fragment commented with to do is more likely to be a true bug. So the central question is how to incorporate such information in a formal program analysis. And this is a non-trivial problem due to the three main challenges. First is soundness. Informal information provides no soundness guarantee. Such information is a hint but not a fact. We cannot treat it as absolute truth. And second is usefulness. A vast amount of informal information is irrelevant to any specific analysis goal. We need a way to identify and leverage the useful signals. And third is automation. To make the approach practical, it must not require significant manual effort. We need a scalable and automated way to extract and integrate these hints. And then I will use a motivating example to walk through our approach and explain how it resolves the three main challenges. Here we have a simple Java program performing a points-to analysis. We have an animal interface with dolphin and dog implementations. And then a wrapper object's content field is first assigned a dolphin object and then overwritten with a dog. The variable dog1 then retrieves this content. And the data flow suggests that variable dog1 points to the dog object created at line 2. There are two type-down casts in this program. One at R1, casting dog1 to a dog, which is a safe cast. And another is at R2, inside the describe method, casting the parameter to a dolphin, which is unsafe. And the instance analysis is flow insensitive, so it will think dog1 can point to the dolphin object created at line 1, and then identify R1 as an unsafe cast, which results in a false alarm. By applying the above data log rules, we get a derivation graph. And as I analyzed before, the analysis derives two unsafe downcasts. This results in a true alarm for the cast dolphin, but a false alarm for the cast dog. However, we notice that the analysis reports the false alarm because it thinks dog1 may point to the dolphin object created at line 1, which means that dog1 alias with the variable dolphin. And similarly, for the variable dog and animal. But for a human programmer, it is more likely that dog aliases with animal, but not dolphin, since a dog is an animal, but not a dolphin. That is, we can predict whether a pair of variables alias with each other by their names. Now, by corresponding informal information to specific program facts, we can leverage the useful information. And to handle the uncertain nature of this information, our approach is built on Bayesian program analysis. So what is a Bayesian program analysis? It is an analysis paradigm that calculates the probability of alarms by converting the analysis into a Bayesian network. And it can incorporate external information as evidence to update the probabilities. This framework first converts the derivation graph into a Bayesian network by attaching probabilities to the data log rules. Here, for deterministic rules, we attach a probability of 1. And for approximate rules, we assume they have a probability of 0.9. And in practice, the rule probabilities can be obtained by training. It then calculates the marginal probabilities of the alarms and gets an alarm ranking. Initially, without any informal hints, the two alarms have a same probability of 0.9, making them indistinguishable. The core idea is to then observe evidence derived from our informal information to update these initial probabilities. And this allows us to reevaluate the likelihood of each alarm and produce a posterior ranking. In the process of Bayesian program analysis, only the ranking, but not the alarms themselves, is updated, so it provides us soundness guarantee. And here comes the central question: how to incorporate the informal information as evidence? In previous Bayesian analysis works, a user is given by an alarm and inspects whether the alarm is true. The user feedback is then set as an evidence, which is either true or false, and we call this as a hard evidence. So one would probably ask, can we just take the previous approach and substitute the user feedback to our informal feedback? For example, we can use a neural network to predict whether the alias relation holds by their variable names, and incorporate them as a hard evidence. But our answer is no. The main difference is that a user feedback is with high confidence, but the alias relation predicted by the variable names is a noisy information. In other words, we cannot definitely say whether two variables alias with each other only by their names. However, using hard evidence will lose such noisy information. In fact, what we consider is something like more likely versus less likely, rather than a simple yes or no. And in order to solve this problem, I then introduce our key technical contribution, soft evidence. So now I will introduce how the soft evidence mechanism is adopted. First, we can assign a confidence value for each alias tuple, given their variable names. And in our work, the confidence is get from a neural network, which I will talk about later. We can see that the confidence for alias animal dog is larger, meaning that it is more likely for dog to alias with animal. If we consider hard evidence, for example, we can set a threshold, say 0.5, and any value above it will be set to a positive hard evidence, and its posterior probability will be forced to 1. But how to set the threshold is tricky. In such case, both the two alias tuples will be set to a positive evidence, leading to no difference. So instead, we adopt a soft evidence mechanism. Rather than forcing a fact's probability to 1, soft evidence adjusts it by a Bayes factor k, which increases the odds of the fact being true. And for implementation, we encode a noisy sensor T prime to the soft evidence fact, and the soft evidence on T will be equivalent to the hard evidence on T prime. The confidence of the alias tuple is assigned to the conditional probability, and then converted to the Bayes factor. The more confidence we believe the alias tuple holds, the larger the Bayes factor is, and the larger its posterior probability is. After applying this soft evidence, the Bayesian analysis updates the alarm probabilities, and now the true alarm comes first. And here I will discuss about how to calculate the confidence value for the alias tuple using a neural network. To predict the likelihood of an alias relation, for instance, between dolphin and dog 1, we take the variable names as input. And then we use a pre-trained model, graph called BERT, to generate the semantic embeddings for these names. These embeddings are then fed into a simple, fully connected network that outputs a probability for the alias relation. For any program fact and its related informal information, we can use a similar framework to predict its likelihood. With the neural network and the soft evidence mechanism together, we can now automatically extract the informal information. So let me summarize our complete approach dancer. We start with a program to be analyzed. The Bayesian program analysis framework constructs a Bayesian network and calculates an alarm ranking. In parallel, our trained neural network processes the informal information extracted from the code to generate soft evidence. This soft evidence is then used to refine the probabilities of the alarms, producing a posterior ranking, and the Bayesian program analysis and the neural network can be trained offline. So here comes our evaluation. And we instantiated Dancer on 2 analysis tasks, a pointer analysis for Java and a taint analysis for Android apps. We ran our experiments on 8 Java benchmarks and 8 Android apps. The informal information we considered was variable names for aliasing in the pointer analysis and string constants for identifying intercomponent communication in the taint analysis. Our neural network was trained on a set of small programs demonstrating their ability to generalize. And I will use a small example to explain the informal information used in Android taint analysis. And in Android apps, different components can communicate with each other by intents. If the action field of an intent matches the intent filter of another component, then the intent can communicate to it. and the tainted value can propagate to another intent by intercomponent communication. And in this code fragment, the action store is get from a config file, and a static analysis tool cannot get it directly. Here, we can get the action field of intent I1 and I2. We can use the string constant fwidget update to predict I2 is more likely to match with the intent filter. And this chart shows the invariant count of alarm ranking, a metric where lower is better for both Java and Android benchmarks. There are 3 bars for each benchmark. The first is baseline, which is the vanilla Bayesian analysis without evidence. Our approach in orange considers the soft evidence. And the rightmost one is the Oracle method, where the ground truth label is served as a hard evidence. We can see that for most benchmark, our approach is significantly better than the baseline, and even close to the Oracle. Then this table shows our improvement on invariant count, mean rank, and median rank, 3 other metrics for the ranking. And the results show that our approach can significantly improve the quality of alarm ranking by taking soft evidence from informal information. We also tested the sensitivity of NISA to different training sets. We divided the 8 benchmarks into 4 groups, and each time we use 1 group for training and the other 3 for testing. We found that our approach is robust. The choice of training set does not dramatically affect the outcome, and performance is stable and generally improves when more training data is provided, which is a desirable property. In addition to the informal information, the soft evidence framework can also be used to integrate dynamic information from test runs. Specifically, we make an evidence for the program fact, which is being tested. If we observe it in a test run, then we set a hard evidence on it, which suggests that it must hold. Otherwise, we set a soft evidence on it. And the more test runs we have, the more confidence we believe it does not hold. We evaluate the dynamic information on interval analysis and a taint analysis for C program. We compare our approach with DynaBoost, another analysis tool that incorporates dynamic information, but it does not provide a systematic way to incorporate such information. The results show that our approach is comparable to the state-of-the-art tool DynaBoost, but more systematic than it. So in conclusion, we have proposed a new paradigm that systematically combines formal and informal information in program analysis. And our core contribution is the use of soft evidence to integrate hints from a neural network into a Bayesian analysis framework. And our work is the first to integrate soft evidence in Bayesian program analysis. We also incorporate information from test runs using the mechanism. Our evaluation on Java pointer analysis and Android taint analysis confirms that this approach significantly improves the quality of alarm ranking. And thank you for your attention. And the code is available on my GitHub page.
Thank you, Tian. Any questions?
That was very nice. In your evaluation for Java, you had an FTP benchmark. That was the last benchmark on the right.
Okay.
And well, what I want to ask about is that it looked like the result there was better than the ground truth in other method based on ground truth, and it looked very different from the other ones. Yeah, see,
yes.
See how top right corner, right? What's going on there?
So in our evaluation, the poster ranking is somehow depends on how the evidence is set, and there may be some wrongly generalizable for the Bayesian network, and it is somehow depends on it somehow depends on how the Bayesian network inference converts. So it may be because of different reasons.
Okay. So is the soft evidence only limited to the variable name aliasing right now, or are you also leveraging any information in the comments?
Oh yes. So I have so actually we propose a principle for how to incorporate the informal information. So, and for other kinds of informal information, the principle is the same. So, for example, you can find some relations that are corresponded to the comments. Say that you and in some previous work, it's someone has used comments, interrupt-related comments, to identify whether interrupt bug is found. So, yeah, maybe the principle is the same.
Yeah. Let's thank the speaker again. Switch. All right. The third talk will be given by Aditya Anand from IIT Bombay. He'll be talking about combining static analysis and speculation. Aditya.
Good afternoon, everyone. My name is Aditya Anand. I'm a PhD scholar at IIT Bombay. I'm going to talk about our work, COSJIT, combining static analysis and speculation in JIT compilers. This work was done in collaboration with IIT Bombay and IBM Canada. As most of you here might be aware that JIT compilers often tends to do imprecise analysis due to its budget. So, some of the recent works tried to do static plus dynamic analysis, where they offload the costly but precise analysis to the static time. The idea is that you offload the analysis ahead of time and then use the results to perform more optimizations. We had a work at last year at PLDI where we talked about how do we optimize object allocation in case of Java. We looked into the optimization called as stack allocation, where we allocate method local objects on the stack frame of its allocating method rather than on heap. The idea was to offload the precise escape analysis to static time and then optimistically use those results to perform stack allocation at runtime. Note the keyword optimistic, as there are dynamic features offered by the language or the runtime, such as dynamic class loading or hot code replacement, which can change your code and can invalidate your static analysis results. To ensure functional correctness, we made sure we had some runtime checks. So, we included some efficient runtime checks to determine whether the static analysis results which we are using are currently corresponding to the runtime environment or not. If not, in that case, we use the idea of dynamic heapification. So, this was one of the first approach to soundly and efficiently use offline or static analysis results in a JIT compiler. Having this background of using static analysis result for improving the runtime optimization, let's look at some of the cases where a JIT compiler can do better compared to just relying completely on a static analysis. For example, the VM maintains various profiling information, ranging from basic invocation counts, loop invariant values, branching information, instance of checks. It also maintains dynamic class hierarchy, which talks about which all loaded subclasses for a particular class is present. It also maintains inlining table, which gives you information of list of methods that got inlined at a particular call site. With all this information, JIT is able to do pretty standard speculative optimization. Why I say pretty standard? Because when you do speculative optimization, you need a fallback. And in most of the scenarios, the fallback is often discarding the generated binary and falling back to interpreter. Now, for the object allocation optimization, since we have an efficient fallback, which I just mentioned, is heapification. How can we get the best of this static analysis and runtime information? Can we make JIT compiler go more aggressive in terms of performing stack allocation? And that's where this work comes into picture. The idea is we will, instead of generating conservative results statically, we will enrich the static analysis with possibility of speculation at runtime. And then we enable the JIT compiler to perform speculative optimization based on the static analysis result. Let's briefly look at some of the cases where we try to enrich the static analysis. The first case is about the way we handle invocation statement is regarding polymorphic call sites. Consider this code example. We have three classes, class A, class B, and class C, where class B and class C are extending from class A and overriding the method bar. At line 14, we have a polymorphic call, and based on the receiver type, the corresponding bar method will get called at runtime. If you notice in class C, the bar method in class C, at line 22, we are storing the parameter into a static field, the global, which is global, and which makes the parameter that is being passed go out of the scope of the allocating method. So while doing standard static analysis, the generated result for method foo will take meet at this call site, and it will take a meet for both the callees and generate escaping for the passed argument. Here the passed argument was 05, and a field reachable from 05 is 07. So standard static analysis will give escaping for both of this object. Now it might happen that at runtime, the dynamic class hierarchy table shows that the class C is not loaded itself, which means that the reason why we were marking the object as escaping is not present itself. So we can go ahead and still can do stack allocation. Even if class C is, let's say class C was present, and the runtime profile shows that class B is taken most number of the time, and hence we can still do stack allocation in most number of the cases. And to encode this information in static analysis, we generate this kind of additional conditions. So we call it as polymorphic conditions, where we say that at line 14, if the receiver object Z type is B, you can go ahead and allocate object 05 and 07 on stack. That's what we do. The second condition is about the way we handle control flow. So similar to the previous case, now let's see if an object is escaping in one of the conditionals. Let's say in the else branch here, the object is marked for escaping. Similar to the previous case, again the standard static analysis will take a conservative approach and mark object 06 as escaping. Now to again encode this information, that it might happen that at runtime the other branch is taken most number of times, we add an extra condition for branching, where we say that if this is the branch which is taken most number of the time, you can go ahead and mark it for stack allocation. The third case is regarding the way method inlining is handled. So static analysis doesn't consider the possibility of method inlining at runtime. Now consider this code example where we have a method bar in class B, and at line 13 we are creating a new object and storing into parameters field. This object is escaping just because it's being stored into parameters field, and standard static analysis will mark O13 as escaping. It might happen at runtime this gets inlined at various call sites. Here it can get inlined at line 4. So what will happen is, right now in method bar, the object O13 was on heap, and if bar gets inlined in method foo, O13 becomes local to method foo. And now if foo is not making O13 escaping, you can allocate this O13 on the stack frame of method foo. To have this encoding again, we generate additional condition saying that at line 4, if the method b.bar gets inlined, you can mark O13 for stack allocation in method foo. This way we allow some of the callee objects also getting stack allocated on caller's stack frame. To summarize, now for our static analysis, along with direct stack allocation results, we also generate these conditional stack allocation results for different cases. And once we have these results, we pass this information to the JIT compiler. In the JIT, we basically bring out all the profiling information as well as like class hierarchy table, dynamic class hierarchy table, profiling information, and use the conditions which we generated statically to get the final outcome. So we have left some holes which can be resolved at runtime to get better results. The algorithm, the in detail algorithm is present in the paper. You can have a look at it. Our evaluation is, our implementation is done in like the static analysis is done in Suite framework, and the runtime component is present in OpenJ9VM. We used benchmarks from Decapo newer as well as older benchmarks. We also used SpecJVM benchmarks. We had two schemes, the baseline scheme where we use the existing escape analysis which is present in the JIT compiler as the baseline, and then the cost-JIT approach, which uses direct as well as conditional scheme. Let's look at the enhancement in the stack allocation. So here we have both these schemes present, the baseline as well as the cost-JIT. And if you look at some of the benchmarks, let's say graph G, you see the static count goes from 12 to 109. This represents the number of allocation sites that were marked for stack allocation. Similarly, the dynamic count, which were the actual number of objects that got stack allocated, improved from 5.2% to 14.2%. Similarly, this number of stack bytes that actually got stack allocated also improved from roughly 8.3 GB to 20 GB. As we were using speculative optimization, we saw some heapifications happening when our speculation were going wrong. On an average, we saw an improvement of 1.4 times in stack allocation, and then an improvement of 5.7 times in stack bytes. This means that this much of less heap memory we allocated. We also measured the garbage collections. So let's look at one of the benchmark. What we did here, we varied different heap sizes, starting from the minimum heap size required for that benchmark, which is represented by X. Then we extended it to 2X, 3X, and the def is the default heap size present. We saw consistent decrease in number of times the GC cycles were invoked for most of the benchmarks. And on an average, we saw reduction of 35% at the minimum heap size. We also tried to measure the performance improvement. We saw a little bit of performance or standard performance improvement for most of the benchmarks. And on an average, we saw an improvement of 6.7%. We also tried to find out the contributions that were made by different schemes. And we saw that there were noticeable contribution for most of these speculative conditions which we generated. So to summarize, we presented an approach where we enriched the static analysis with possibility of speculations at runtime. We gave a mechanism to have to incorporate these conditional static analysis results in the JIT compilers. And overall, this was one of the first approach that tries to create a balance between static analysis and speculation, harnessing best of the both worlds. You can have more details in the paper regarding what were the overheads, how do we handle different conditions in more detail with examples, and how it is different from other VMs. We try to compare with one of the VMs as well. You can find more details in the paper. Thank you.
Thank you, speaker. Any questions? While the questions are being answered, the next speaker may. Yeah.
Very interesting work. I have a question that does the speculation are always correct, or if the speculation fails, how do you handle this in this approach? For example, the de-optimization by JIT or something else?
Yeah, so as I mentioned, we had a fallback mechanism called as heapifications. So we have these checks present at all the places where possibly, if you are using static analysis result, possibly the static analysis is going sound. So similarly, if you are using speculative results, those heapifications checks can still be valid, still be used as a fallback options.
Okay, thank you.
Any other questions? No? I had a very super quick question. So if you have a conditional branch, if else,
right,
and else was executed only once,
right,
first time, and the next 1,000 times if was executed,
right,
but the global is already escaping the object, right, because of the else branch. So, I mean, I was just thinking of the intuition behind saying the if branch is executed most of the time, hence allocated locally. The intuition behind that, such a check.
The intuition is that the profile data is showing us that the if branch is taking most number of the times, and we hope that in future as well it will continue to do so. That's the hope, and that's the intuition, and on that intuition we try to locate.
All right. Maybe you can ask the question and he can answer without the slides. Yeah, go ahead.
To see if your situation is what you had in the static analysis. What are those checks typically? I'm wondering how advanced, how big, how much time consuming they are.
Yes, so those checks are at all the places where possibly an object can escape. Let's say an store statement can make an object escape. A return statement can make an object escape.
And what is it you check then?
So we try to see whether, let's say at a store statement, if you are storing into a field, if an object's field, whether that object is on heap or not.
whether
If it
it's
is
in the
already
heap or
on
not.
heap, that means that if we have done stack allocation, that's wrong.
How many cycles does it take to check that?
Sorry?
How many cycles does it take to check that?
How many cycles in terms of?
Of just checking time to check that condition.
So we tried to measure the heapification checks cost. There was some overhead, but it was pretty low compared to the performance improvement which we got.
Very good. Okay, that's what matters.
Thank you.
All right. The next talk will be by Yuanfang Shi on abstraction refinements for a Bayesian program analysis. From Peking University.
Okay, thank you. Hello, everyone. I'm Yuanfeng Shi from Peking University. I'm going to talk about our recent work on abstraction refinement for Bayesian program analysis. This is a joint work with Yifan Zhang and Xin Zhang. We begin with an introduction to Bayesian program analysis, which is a new paradigm to address problems existing in conventional program analysis. Analyzer will generate alarms based on logic rules and provide them to the user. However, there are many false positives due to the approximation. The analyzer also cannot learn and adapt to the user's needs because the logic rules are fixed. To address these problems, Bayesian analysis converts conventional ones into Bayesian models. As a result, it can learn from posterior information such as user feedback, order version code, and test runs. It can also generate the probabilities of alarms to rank them. Therefore, compared to conventional analysis, it can significantly improve users' experience. Next, let's focus on the key component of program analysis, abstraction selection. For conventional one, there is a trade-off between precision and scalability here. Moreover, for Bayesian one, abstraction also heavily affects its generalization ability, which means its ability to learn from posterior information. So, how to select proper abstractions to achieve a balance between precision, scalability, and generalization becomes a challenge. To address this issue, our group proposed an offline learning-based approach, but it may work not so well, especially when the new program is out of the distribution of the training set. And inspired by the CIGAR technique, in this paper we propose an online approach, and I will use an example to explain it. Here is the example program. Method input 1 always generates odd numbers, while input 2 always generates even numbers. A data flow analysis is applied to resolve potential division by zero alarms. Here the divisors in x1, x3, and x5 cannot be zero as they are all odd. But for x2, x4, it is possible as they are even. And we additionally assume the analysis doesn't know the specifications of input functions. Hence, those functions can produce any integer, and this numeric analysis will degrade to a tent analysis. Then we can cast it as a graph reachability problem as shown by this figure. And we should conservatively assume data flow from both input 1 and input 2 are tented. Then the directed edges denote data flows in the program, and the analysis will report alarms for x1 to x5 as the tented data flow from I1 and I2 will reach them. However, as you can see, such approximation introduces false alarms here, x1, x3, and x5. So in Bayesian analysis, we can attach a probability 0.99 to each variation to quantify their degrees of approximation. Note that such probability can use machine learning tools to assign. Here we just use 0.99 for our illustration. For example, if tent I2 is true, then the probability of tent Y being true will be 0.99. After that, the whole graph is transformed into a Bayesian network, and each tuple becomes a random variable. We can do Bayesian inference on each variable based on given posterior information like user's feedback. For example, we can first calculate the probability of A1 to 5. Here, alarm xi is simplified as AI. For A1, A3, A5, we all have the same highest probability. Therefore, the user checks A1 and gives a negative feedback. Then, based on that, we can calculate the conditional probability under this feedback. The probabilities of A2 to A5 all decrease since the negative feedback will blame them common father node tangent I2 here. This is not good for the user since you can say the ranking order between A2 to A5 does not change anymore, and the user needs to inspect all the 3 false alarms to discover all true alarms. The true alarms are below those false alarms. So, to address this issue, our solution is to perform counterexample guided abstraction refinement. Here, the counterexample refers to those alarms whose probability drops are undesired. Take A2, for example. It is a true alarm, but its probability dropped after generalization. Hence, it is a counterexample. We find such a counterexample by sampling alarms whose rank drops the most. Here, rank drops of A2 to A5 are the same, and we sample 2 alarms, A2 and A3. Then we ask the user to inspect A2 and A3 and discovers that A2's probability first change and A3 correctly change. Now the target of our abstraction refinement is to remove information transmission from A1 to A2, but preserve such one from A1 to A3. This can be done by inlining read input even at 910 and separating a corresponding node tangent I2Y here. But another question comes. How to model such information transmission to guide our refinement? It needs a formalization to guide this refinement. Can we model just such transmission as a simple graph reachability problem? Okay, but our answer is no. Let's look at some Bayesian networks. Here, if A is read, then A is an apple with probability 0.5. If A is an apple, A is delicious with probability 0.9. Then given feedback that A is indeed delicious, the posterior probability of A being read will increase. However, if A is observed to be an apple, the feedback will not affect the posterior probability of A being read anymore. This is because such transmission is blocked by this observation. Another example is illustrated here. Here, otaku refers to those people being addicted to animes, idols, and all other possible things. Here, we offer 2 main courses, anime and idol, and I will show the type of my friend, Sky. Because please note that whether Sky is addicted to them are independent without any observation. However, now Sky is confirmed to be an otaku indeed, but I know that he didn't love idol. Then we can easily infer that the probability of Sky loving anime will rise, which shows that given this observation, those 2 events are not independent anymore. Therefore, the transmission of posterior information is not a simple reachability problem, especially when we're considering observation. And the theory of conditional independence answers such problem. Here the arrow from X to Y means that the information from X can reach Y. For more details of the theory, you can refer to our paper. Here, we just use this theory to construct the information transmission graph for our example program. And our problem reduced to cutting off A1 and A2 in this transmission graph while preserving such connection between A1 and A3. However, such problem to seek a min cut to separate a pair of nodes and meanwhile ensures the connection between another pair of nodes has been started in a previous work, which shows that it is NP hard. Therefore, we just reduce it to a partial weighted max set problem, and then we can solve it using a max set solver. The details of such reduction are also given in our paper. You can refer to that. Finally, with the information transmission graph, it is easy to say the cheapest way is to remove one edge on the path tangent I2 to tangent 1 and to alarm X2. It can be realized by inlining the corresponding node tangent I2Y. After such refinement, those true alarms and false alarms are divided, then the ranking of A4 will shift to precede A5. Although the user needs to inspect A3 during sampling, the number of observed false alarms reduces from 3 to 2. Note that our refinement is the most efficient and proper to divide those alarms. For example, if we just inline, we'd input even at 9, and encode it as node 10 to I21. It is easy to say we cannot divide those alarms, and it is bad. Finally, we show the workflow of our framework-based refine, which is an abstraction refinement module atop a previous Bayesian program analysis system, Bingo. It will first sample several alarms for the user to inspect, and then just use these inspections and leverage the conditional independence theory to construct an information transmission graph based on the derivation graph. Last, we can just refine the abstraction and change the structure of the derivation graph, then start a new iteration. In order to evaluate the efficiency of our approach, we conducted experiments on it. We used 2 instance analysis, a data risk analysis and a threat escape analysis. Our benchmark consists of 12 Java benchmarks from the decouple suite and from past works. Our baselines are running Bingo without refinement using abstractions produced by BinGraph, which is our previously proposed offline approach. Our major evaluation metrics are also offered here. We first researched how effective is Bayes refine. First, our results show that Bayes refine improves BinGraph's performance on both 2 metrics and 2 instance analysis. In summary, Bayes refine is indeed effective. We also evaluate how effective Bayes refine is under different training sets. Here, FTP GSpider and FTP HEDC use different corresponding programs in the benchmark for training. And we discovered that when the training set selection is suboptimal, the improvement is even more significant as shown by those reduction. And from the perspective of machine learning, Bayes refine can be regarded as a structured learning approach, and we also compare it with a parameter learning approach, Bayes Smith. And the results show that while the reduction of parameter learning alone is less than structured learning alone, combining them produces the best results, which indicates that they are complementary. Last, we researched whether Bayes refine is efficient enough to scale. We discovered that a refinement module incurs little overhead here, as shown by refinement time, while the average Bayesian inference time also decreases. Moreover, we researched the data log-based analysis after refinement, and we discovered that the abstraction is not refined too much. Finally, I will give the conclusion of our work. First, we propose an online abstraction search framework that is akin to CIGAR to solve the overgeneralization problem. Next, we propose a technique that identifies the abstraction to refine by leveraging the theory of conditional independence. Last, we evaluate our approach with 2 realistic analyses and demonstrate improvements to our existing offline technique. That's all. Thanks for your listening.
Thanks for the talk. Do you use the results of the analysis to also perform some optimizations? For example, the results of the thread escape analysis, were you able to translate them to, let's say, remove locks or any other dependent optimization?
Excuse me, you mentioned a thread escape analysis.
Yes. So once you perform the analysis, you got improvement based on refinement.
It is a coarse analysis. We just model all heap objects as an abstract node, and it is just for testing. that if you want to refine that, you just drop that heap object from that closest abstract node and drop it and form a new node in the graph.
Okay, so it's basically analysis and not optimization, right? Yeah. Okay, that solves the query.
Thank you so much for the introduction. Thank you so much for being here. Here we're going to talk about static analysis, MLIR, and crucially automatic differentiation. This work is done in collaboration with William Moses and Alexander Zinenko, in addition to my supervisor, Christoph Dubach. Okay, so to motivate this talk and to motivate automatic differentiation more broadly, the computation of gradients is ubiquitous in the fields of machine learning and scientific simulation. It's perhaps, well, controversially most well known in the training of deep neural networks, but it's also used in all sorts of like these inverse problems where we have this billiard simulation where you have some initial parameters for your simulation, namely the angle and the amount of force that you apply for your ball. And then you have some target state, which in this case, you want to get the red ball as close as possible to this blue position. And you can backpropagate using derivatives, using automatic differentiation to find these initial parameters that best matches your desired target state. The process of automatic differentiation allows you to automatically generate programs that compute derivatives, and it's very flexible in general, but there are certain limitations with it. Two key limitations are that the generated derivatives tend to be a performance bottleneck. And the second is that there are certain usability challenges that we'll see shortly. Okay, so to talk about these usability challenges, traditionally, the wisdom is that in AD, every part of your program needs to be differentiable. So some pseudocode that kind of describes the physics simulation from before is that you iterate through a bunch of time steps, and then at each point, you advance the simulation forward, and then you also visualize it by rendering it to the screen. However, you might see that an AD system, especially an AD system like Enzyme, might find that you have certain programs that you don't have registered derivatives for, at which point the system will crash because it says, I don't know how to differentiate this. However, you might notice that we're interested in the physics of the problem, but we're not necessarily interested in the obtaining derivatives of all of this rendering OpenGL code, even if it is theoretically possible to obtain these derivatives. So the question is, can we safely ignore parts of our program that are irrelevant? And furthermore, can we ignore these parts of our programs without compromising the correctness of the derivatives that we do care about? The answer to this is this standard technique that's used in autodiff systems called activity analysis, where it improves the usability and the performance of our generated programs through differentiation by ignoring these irrelevant instructions. Prior work in activity analysis has a number of important limitations. The first is that there isn't a correctness guarantee, meaning there isn't like a formal understanding of how to guarantee that our derivative is unaffected by removing these unnecessary instructions if they're truly unnecessary. And the second is that many AD systems have restrictions on the input language that are permitted. For example, if you're using the machine learning library JAX to do your differentiation, you'll need to rewrite your programs if any of them use mutation. There are other systems like Tapenad where you need access to all of the source code being differentiated. And then if you are missing any particular modules, like would be in the case if you're differentiating black box libraries, you'll need to make very conservative guarantees, and the analysis will over-approximate these. So our contribution addresses these limitations by having the following three properties. It is sound, modular, and general. The soundness is done by formalizing our analysis as an abstract interpretation and including a detailed correctness arguments. As part of this, we formalize the language we're operating on, MLIR, which we'll talk about in just a second. The second is that it's modular. So it relaxes this restriction of needing a global view of all of the source code that you're differentiating. Instead, it uses function summaries, which is this established approach, and then our contribution is the design of the precise summary such that it can be used in any calling context. Unfortunately, for the sake of time, we probably won't have time to go through the details of this function summary, but those are in the paper. And the third is that it's general. It supports MLIR, which is this compiler infrastructure that is not finite because it's extensible and therefore new operations are always being added to it. Okay, so to talk about how activity analysis can improve the performance of differentiation, assume that we have this function which has 2 inputs and 2 outputs. And we are interested in the partial derivative of one of the outputs with respect to one of the inputs. The process of automatic differentiation will yield this generated function, which actually computes a vector Jacobian product. Because our function is 2 inputs, 2 outputs, the full derivative, so to speak, is a Jacobian matrix, the 2x2 matrix. And the process of especially reverse mode automatic differentiation will give a general way to extract rows of the Jacobian by changing these additional parameters, the DC and DD. In particular, we're interested in the entry at the left, the top left corner. And to do that, we can set DC to 1 and DD to 0, which hopefully you will see. You perform this vector matrix multiply, and then you get the result that you want. So now we can take a look at an example implementation of what this function might be. And the process of AD, well, for starters, our function has this expensive loop which iterates a bunch of times, does a bunch of work, and it computes the second output, but this loop doesn't matter for the first output. A consequence of this is that when we perform differentiation, the loop results in a loop that iterates in reverse. Effectively, at a very high level, we're kind of iterating through the loop in reverse. And we're doing a bunch of work, but as we saw, because we're only interested in certain partial derivatives, we will call this function setting DC to 1 and DD to 0. And then on line 13 and 14, we're multiplying DD with another value, which will yield 0. We're adding those. In total, this reverse to loop is adding in and multiplying a bunch of zeros and not meaningfully contributing to the partial derivative that we care about. So AD gives us this very general method for computing all of the potential partial derivatives in the Jacobian matrix, but depending on your application, not all of them will be relevant. And activity analysis is a way to communicate this to the system statically at compile time such that these loops won't even be generated in the first place. The sort of high-level intuition for activity analysis is done by reasoning about differential data dependencies as they flow through the various variables and memory allocations in your program. The user will annotate the function being differentiated by saying some of these inputs are active and some of the outputs are active. Then any variable or memory allocation is active if and only if it lies on some path from an active input to an active output. Okay, shifting gears. Why do we target MLIR? And what is MLIR? As I mentioned, it's an extensible compiler infrastructure, which means that it's a language that new operations are continually being added to it. Currently, MLIR is used for a number of things like tensor algebra. It's used a lot in stable HLO, which is used in XLA, which you may know as powering JAX. It's also used in domains such as polyhedral compilation and in quantum computing. This is only like a small sample of the cool things that people do with MLIR. People also use it for like hardware design and other things that are not coming to mind at the moment. And again, like new dialects are being added all the time. And so it's very powerful, there are powerful representations, and we would like to differentiate any MLIR. But then this creates this problem of how do we write an analysis that can grow alongside a growing intermediate representation, a growing language. To do this, we use this concept in MLIR of interfaces. So MLIR includes a number of operations, but we kind of simplify and extract only the necessary pieces of information that we need in each operation. There's a bunch of different ways to have a memory load, and there's a bunch of different ways to allocate memory. There's a bunch of different types of computation that can happen, like a multiplication, but also a convolution or a matrix multiplication. All of these are kind of categorized into these interfaces that extract precisely the information we need to run our static analysis. Okay. Now, we measure the efficacy of our activity analysis by looking at a number of things, including the runtime speedup. So Enzyme is the automatic differentiation system that all of this is built into, and it has a prior activity analysis that does not have the same soundness guarantees as this work, which is labeled informal. And then we have two variants of activity analysis done in this work. One which assumes that you have access to all of the source code being differentiated, and another which operates function by function and then only communicates via function summaries operating in this modular fashion. We can see two takeaways. The first is that activity analysis has a non-trivial impact on the performance of the generated derivatives, in some cases up to a 3x speedup, and geomean about a 24% improvement and a 70% improvement, respectively, on the CPU and the GPU for the benchmarks we looked at. The second is that our sound analyses don't lose any of this performance improvement relative to the prior potentially unsound analysis. So formalizing and making our analysis sound did not cost us performance. Another result is that we looked at the various precision of these variants, and although we didn't have time to go into the details of how the modular analysis works, we see that it doesn't lose any precision relative to having access to all of the source code in the program. The third is that we compared the compile time performance of our modular and our whole program analyses. And we see that for smaller benchmarks, the modular analysis has a slightly higher compile time overhead per function, but it does less work as the benchmarks increase in size, which is the case for our GPU benchmarks, which have thousands and thousands of functions in them that are being processed. And we see a significant compile time speedup as a result of our modular analysis relative to the whole program analysis. Okay, so in summary, the computation of gradients is very useful and widespread, but AD can be a performance bottleneck and be difficult to use. So activity analysis enables these faster and more general differentiation procedures by avoiding unnecessary instructions, and this work builds on that by formalizing activity analysis, proving it sound, and generalizing it to work on arbitrary dialects and also mirror the extensibility of MLIR. There's many details that are not included in this talk but can be found in the paper, including detailed operational semantics of the subset of MLIR with which we operate, and full details of how everything is formulated as an abstract interpretation, the function summary design and proofs as to how you can get just as good results with the function summary instead of looking at all the source code. And then there's full correctness proofs for everything mentioned. All right, thank you so much.
Any questions? Okay, while the audience is warming up, may I request the next speaker to be ready? Yeah, I have one question for you.
Yes.
So if I have a function which has, where you are creating the summaries for functions, right?
Yes.
If the function has other function calls which are not easily resolvable, say function pointers or virtual calls, how do you deal with them?
Great question. Regarding indirect function calls, we currently do not. Yes, because it creates a compound problem of trying to resolve like which of the possible call sites are being called. One potential approach is to try to do like a union of the different potential points to candidates of which functions could be pointed to. But yeah, it is challenging.
And good afternoon. I'm Choi Zhang from Nanjing University, and welcome to our presentation of towards the selective backed and practical framework for selective object-sensitive point analysis. And this is joint work with Longlong Lu, Yifei Lu, Xu Pan, and Junong Lei, also from Nanjing University. So I introduce our work following this outline. I first talk about the background and then move on to the key insights and the framework. And next I will talk about the implementation and evaluation. So point analysis basically determines which objects are viable point to at runtime, and it has many clients such as program understanding, program application, bug detection, and security analysis. It has been implemented and integrating many existing static analysis tools like Tile, Suit, Dupe, and Voila. So a precise and efficient point analysis will benefit all the clients and all the tools. So context sensitivity is basically known as a fundamental techniques for improving analysis precision. It distinguishes calling context for each method to prevent the merge of different point values. But here's an illustrative example. We have a class named box, and it has a method named ID, which directly returns the parameter O. And in the main method, we have the two objects, O1 and O2, also two boxes, B1, B2. And next, we call the ID method twice. So this is basically the point flows. And on the context insensitivity, since context of method ID are not distinguished, so the parameter O of ID will point to both the two objects, O1 and O2, and as well as for the two variables, R1 and R2, causing imprecision. And on the context sensitivity, here we mainly refer to the object sensitivity. And we distinguish the method ID by its calling context, and you can see here that the O is replicated under different contexts, so we can have the precise results. But context sensitivity, while it can significantly improve the analysis precision, it also introduces heavy analysis overhead, especially when applied to large-scale programs. So selective context sensitivity approaches are proposed, and its main key site is to eliminate redundant context when it's not helpful to analysis precision, so it can improve efficiency while retaining most of the analysis precision. And existing work try to eliminate the context of different program elements, such as the methods and the variables and heap objects. And among them, the application on heap objects demonstrate an extremely high efficiency gain and with little precision loss. So we believe a clear theoretical foundation for understanding when and how objects benefit from context sensitivity to improve precision remains underexplored. So we propose a framework featuring a theoretical foundation to explain when and how these objects can benefit from the sensitivity, and also a two-step track approximation for practical use. So let's begin our key insights. We first introduce the point flow graph, which is mainly a constraint directed graph where nodes are pointers and objects, and edges are points to relationships. And point analysis can be seen as a reducibility problem on the PFG. So if you can see, for example, in the program below, we have a variable C points to object O, if and only if C is reachable from O on the PFG. And from the view of PFG, we have that in the field-sensitive point analysis, context sensitivity mainly affects objects by replicating their field pointers. So we can basically evaluate the primary effect of an object on analysis precision by check whether its field pointers can successfully distinguish the point flows. So suppose we have a field F of object H, and here we have a PFG snippet. So you can see that a variable V and an instance field H.F and then Z. So the since we are under context insensitivity, the contexts here are empty. And we also have some objects propagate first to the variable Y and then the instance field H.F and then Z. So under the corresponding context sensitivity, which mainly replicates the pointers under their contexts. So the same PFG may demonstrate in different potential scenarios, and here we list mainly the 3 representative ones. So let's look at the case 1 first. It has mainly the 2 important structures, which the first which is distinctive flows. So here we have 2 point flows, the one carrying the object O1 and the other one carrying object O2. And also, we have the partial connection before and after the instance field. So these structures are key to separate the distinctive flows. So, and this brings us the preceding improvement. But in contrast, in case 2, while we have the same distinct point flows, we also have a full connection before the instance field. So the 2 distinctive flows merge together after passing through the instance field. And in case 3, we only have 1 point flow, so making the further differentiation actually unnecessary. So while the distinctive flows are easy to follow, you may wonder under what situation will the fully connection happen. So we have a field stone statement of Java corresponding to this PFG snippet, and it has a variable base and field access through its field f and a variable y stone to this field. And by the analysis rules, we have this fully connection happen if and only if the 2 contextual versions of the variable base point to both the 2 contextual objects of object H. So this is actually a very insightful and important property in our framework, but since it's due to its intrinsic complexity, we do not dive into the further details here, and we kindly refer to our paper for full discussion. So we can basically conclude our key insights as an object is procedure relevant only, and if only, under context sensitivity there exist both these 2 key structures involving one of its field pointers. And note that we have fields and pointers actually the same under, can be seen as the same under object sensitive analysis. So next we only talk about the field operations and without loss of generality. So I'll talk about the framework next. So we basically gave the first, basically given the definition of ground truth objects. So these objects are whose context sensitive treatment actually improves precision on the context sensitivity. But since the direct computation of these objects are infeasible in reality, so we propose a first some upper bound approximation we define as procedure relevant objects. As you can see, it can be divided with 2 key parts and corresponds directly to our 2 key insights. Also, this definition is defined under context sensitivity, so the direct compute is also infeasible, unfortunately. So we propose another further some approximation for practical use with the result of context insensitive analysis. And you can see we decompose the definition with 4 subconditions, and each condition is a necessary condition of their corresponding part of procedure relevant objects we defined before. And we also propose a variable flow graph to enable efficient traversal to identify these objects. So in summary, we propose 3 key kinds of objects to deliver both a theoretical foundation and a practical method for applying selective context sensitivity on heap objects. And next, and finally, we'll talk about the implementation and evaluation. So we implemented our tool named Moon upon the Chilling framework, and its implementation is publicly available as an open source tool. And since it outputs actually a set of procedure relevant objects, so it can be easily aggregated with other static analysis tools. And in the evaluation part, we aim down to 3 key questions. How does Moon-guided object-sensitive point analysis compare to the conventional object-sensitive analysis and other sort of alternative techniques? And in Arc 3, we aim down to what's the computational overhead of Moon. So to ensure a broad range of evaluation, we selected 30 programs from the benchmarks, and recent studies, and also GitHub. And this table lists the details of our benchmarks. So for answer of AQ1, we compare Moon with conventional point analysis. So Moon only selects only 1.6% and 2.9% of all the objects as context sensitive for 2-OBJ and 3-OBJ sensitive analysis here. But such small proportion of objects nearly keeps all the analysis precision, namely 99.9% and 99.8% for 2-OBJ and 3-OBJ. And they also bring us extremely high efficiency for 2-OBJ and 3-OBJ, namely 37.2 times and 302%. So for AQ2, we list the details of precision loss and speed up here for also 2-OBJ and both 2-OBJ and 3-OBJ here. And we can conclude that the Moon achieves an outstanding trade-off between analysis precision and analysis efficiency. Also for the AQ1, we also list the time detail of Moon and other selective techniques. And we also can conclude that Moon demonstrates a relatively low overhead comparing to other sort of tactics. So we conclude our work as a selective foundation, a two-step trackable approximation for practical use. And its implementation demonstrates that it can efficiently and effectively identify these precision-relevant objects. And the evaluation demonstrates that Moon achieves an outstanding trade-off between precision and efficiency. And that's all my work. Thanks for listening.
Thanks for the talk, interesting work. I have two questions.
Okay.
One is, your evaluation seems to be on very old da capo benchmarks. Is that the case?
Oh, sorry, I didn't.
Your evaluation seems to be on a very old version of da capo benchmarks. Is that the case? Okay. Yeah, the table.
Here?
Yeah, these seem to be from 2006. No, you have done it on. So, I mean, there are selected benchmarks from each. Did you do it on all the da capo benchmarks from the latest version?
Since we selected this following the analytic work, and since the wide use of da capo 2006, we also keep the use of it in our paper, and we also include the newest version, newer version of the da capo benchmarks to ensure a broader
Okay, the question I had was because these new benchmarks use a lot of reflection, so I wanted to understand how do you...
reflection, you mean reflection?
Yeah.
Okay, we actually adopted the, if I remember correctly, I adopted the default reflection log generated by a
Okay,
tool.
okay, yeah, that's probably the standard approach. The second question I have is, the 2 or 3 cases that you showed in your examples, they look quite similar to the zipper work as well. But you yeah, correct.
Okay.
But you show improvements with respect to the zipper work in your comparison. So I could not understand how do these cases capture more than the cases covered by the zipper paper that you have compared with. Is there an example that you have where that kind of work will not capture a particular, will not give equal precision, and your work will lead to more precision?
So you mainly ask about the connection between this and the motivated example?
Yeah.
Okay. Actually, they are a little connection. In the presentation, the motivated example serves to illustrate the context sensitivity, and here is mainly serves to illustrate our key insights. So it might be a little hard for you to directly see the connection between, so we can talk about this offline.
Sure. Sounds
Thank
good.
you very much.
Thank you.
Oh, sorry. Could you go?
Okay.
Okay. Yeah. Okay. I was going to ask you to go back to your slide on precision, but I'm afraid that's no longer possible. But you compared precision compared to a conventional approach with context sensitivity. And the precision of your approach was quite similar. I wonder how it compares to a completely context-insensitive approach. Do you also have any number?
You mean compare what? Compare context-insensitive with?
With your approach, like the conventional approach, I think in your charts was a fully context-sensitive one.
Oh, okay.
And the precision was quite high in your approach as well, selecting only 2% or
Yes.
3%
Yes.
of objects for context sensitivity. I wonder just how much precision you would get if you would select 0% basically of context sensitivity if you do a completely context insensitive analysis.
Actually, I have to clear it up. Okay.
Okay, we'll talk about it later. Okay, thanks.
Picking up? Okay, now it is. Hello everyone, and welcome to... sorry. I'm gonna hold it. Hello everyone, and welcome to my presentation of our paper, Universal Scalability in Declarative Program Analysis with Choice-Based Combination Pruning. This is joint work with Anastasios Antoniadis from the University of Athens, Neville Gregg from University of Malta and Didop, and Yanis Maradakis. So, what is our work about? Choice-bound, it's basically a technique for tackling the scalability program that one typically encounters in declarative program analysis, and specifically data log. So, what we do in a one-sentence summary is that we give you a way to limit the combination of certain combinations that you encounter in the analysis, and we found that it's a very effective technique, and it actually eliminates the scalability issues that you would encounter at the cost, of course, of some completeness. So first of all, what is data log? It's a logic programming language, so this means that algorithms are expressed using predicates and inference rules. And it's one key differentiation from other programming languages such as Prolog is that it's evaluated bottom-up. So the engine will take these facts and the inference rules, and it will try to prove everything it can until it reaches a fixed point. So here we have the classic hello world programming data log. We have the edge relation representing a graph, and then we have the reachable relation, two rules, implement those two rules. The first one is just the base case, and then the second one is the recursive case, where we basically apply a transitive closure over the edge relation. Okay, so data log and program analysis is actually an excellent fit, and this is because it has excellent support for recursion. It gives you a very nice language to express analysis algorithms, and it's very easy and quick to prototype into. And a very nice bonus, especially in recent times, is that modern data log engines are actually extremely performant, so you get a very good performance even compared to imperative implementations. But it's not all good, unfortunately, and this is because declarative analysis has some scalability issues, and so this is because some large inputs can cause imprecision to some central relations in the analysis, and combined with the bottom-up evaluation of data log, this leads to execution time blow-up. So one technique that is typically employed in the literature to solve this is pruning. So what is pruning? Essentially, is just we say that we have some sets in the analysis, and we say, okay, I'm going to limit them to some predefined limit n. So to make it more concrete, here we have a table that's like representing a var points to relation. I have colored the table in partitions, so the red ones are the variable 1, the green ones are the rows for the variable 2, and the yellow ones are the rows for the variable 3. And we see that variable 3 actually dominates the table. So let's say we want to apply a pruning policy like this. So we say that each variable can have at most rows. The engine will go and only keep 2 rows per partition, and we end up with a much smaller table, which in turn, of course, gives us much better scalability, of course, at the cost of some completeness. But the problem is that this simple and effective technique, it's hard to express in data log. So this is where our technique comes in, choice bound. It's basically a way to express pruning declaratively in data log, and it's general and engine agnostic. So you can apply it to any data log engine as long as it supports functional constraints. And specifically in our Souffle implementation, we make use of the choice construct. So just to a small note here, choice is the existing feature in Souffle. Choice bound is our new technique. So quick intro in the choice construct. So here we have an example relation R, x comma y, and then we say choice domain is x. So what does this mean? So in Souffle, the choice construct essentially extends data log with non-deterministic choice. So what this means is that at runtime, Souffle will only choose one row for each value of x. So in this example, it will only keep the first one for R x comma y, x equals 1. It will keep the second row for x equals 2, and we only have one inference for x equals 3, so it will keep that one. So this essentially enforces a functional constraint of the relation, basically Rx equals y. Okay, so what is the core idea for technique? So the idea is that we can take this functional constraint mechanism and lift it to express multiplicity constraints. So basically, what I mean with that is that in functional constraints, R of x can only have one value. But what we want to express, in order to basically have pruning, is that we want to say that R of x can have up to n values. Okay, so how do we do this? So first of all, here's a more general relation Q, x comma y and a comma b. We start by declaring it as a function of x comma y. So the choice domain is x comma y. So right now this is very restricting in the sense that there's a unique pair in Q for x comma y. So we need to relax this a bit, and in order to do this we need to augment Q with an extra field I. So this extra field I we also included in the choice domain, so the function domain. And this is an extra degree of freedom that we can play around with. But okay, we didn't do anything special yet. What is this I? The key here is that this I is not an independent variable, but we actually compute it as a function over a comma b, so the codomain of the function. And then we take it modulo n. So let me iterate it again. So we take I is not like any variable. We take the actual codomain, we pass it through a hash function, so it becomes an integer, and then we take it modulo n. So I want to convince you that this actually implements multiplicity constraints. Let's see. So we had the initial version where it was just a function of x comma y, and I want to convince you that the transform version, both with the choice domain change and the inference rule change, that actually x comma y is a multiplicity constraint. So we start by observing that x comma y comma I is unique in the relation Q. And then if you also observe that I takes values from 0 to n, because we take it modulo n, then we can infer that x comma y has up to n I values. But now we also said that I is not just any field, that it's a function over a comma b. So it follows from the above that x comma y has up to n values and a comma b values. So yay, we implemented the multiplicity constraints. So let's discuss a bit about our technique. So our technique is actually very easy to adopt existing code bases. So you can do a semi-automatic search and replace in your code base and introduce it with very little manual overhead. And it actually gives you a very nice language to explore this design space. So you have control over what variables you want to bound, so what fields you want to limit the combinations of. You have control over the limit, so how many combinations of these variables you want. And also you have control over the counting variables, so what fields of the relation are being hashed. So to make this a bit more concrete, let's take this classic var points to relation from the literature. So variable points to heap object under context, and with choice bound we have the ability to explore many different configurations with different trade-offs. So with this configuration, we can say that every local variable can point to at most 500 heap object context pairs, but with a very simple change in the configuration, we can have a very different algorithm, flavor of the algorithm, where we say that every local variable can point to at most 100 heap objects under the same context. So you see the flexibility that this framework gives you in terms of expressing different flavors of the same analysis. So let's go over the evaluation. So we applied choice bound to two existing large-scale frameworks in the analysis. So DOOP it's a Java pointer analysis framework and symbolic value flow. And we evaluated it across three axes: performance, completeness, and robustness. And the main takeaway from the evaluation is that we get impressive speedup at the cost of some incompleteness and non-determinism. But it's not that much, as we will see. So specifically in DOOP, we compared the default two-object analysis to our modified choice bound. This is the setup. I'm not going to stay too much on this. So first of all, the dataset. This is historically a very challenging dataset for DOOP. And here we see that we get a very, very nice speed up to 57 times, with an average of 23. And I want to point out that the speed up, actually, this is a low, it's under approximation, because the speed up we see here is for time. We limit the timeout, the runtime to the timeout amount. So if we let the analysis run to completeness, we will get a much larger speed up. So in terms of completeness, we don't lose too much. We have a modest drop in completeness. So we compare the up method reachability. So we dropped from 63% in the default analysis to 59% to 60%. So this is expected. This is a pruning technique, but it's not that much. It's minor, and we also have the secondary cost of non-determinism due to the choice construct. So due to time constraints, I'm not gonna go into too much time here. So in conclusion, we present the choice bound, a flexible and powerful technique for declarative pruning in Datalog. We discussed the capabilities it offers to the analysis designer in terms of exploring the scalability and completeness landscape with our technique. And we showed that it's actually a really effective way to address the scalability issues of declarative program analysis at the cost, of course, of some completeness and non-determinism. Thank you very much for your attention.
Questions?
Oh, hi, very clear. So you talk about completeness, and I understand that you lose very little in completeness. But then there's also soundness. And so I know that people have opinions about soundness in your group, but do you run any risk of actually losing soundness that you would like to keep by cutting down on the sets?
How do you define soundness? Because
well, to me it means that. To me, soundness means that anything that could happen at runtime is captured by the analysis results.
Okay, so I don't show it here, but part of our evaluation is that we also have, in symbolic value flow, we have some vulnerability analysis. We don't really have a soundness evaluation. Yes, that's what we call completeness.
I see. You call it completeness.
Yes. I mean, it's a dual definition, yeah.
I need to think. I was not one of the reviewers.
Hi, have you heard of answer set programming?
Sorry?
Have you heard of answer set programming?
Yeah, I'm not that familiar, but yeah, I've heard of it.
In my personal understanding, this is essentially what can be done in answer set programming. So the reason Datalog has no such general choice is that it's monotonic reasoning, but answer set programming is extending Datalog with non-monotonic reasoning. That's why they can have the generalized aggregates. You know aggregates in Datalog, right?
Yes, I mean, we do have aggregates. So
yeah, but in Datalog is monotonic, and in answer set programming is non-monotonic. So it can do I can showcase if you are interested in, but in my opinion, is essentially can be encoded in ASP.
I'm sure that answer set programming is more general than Tenderlock, but the main selling point is that we can take existing implementations.
That makes sense.
Do a simple adaptation of the algorithm and get scalability gains. I'm not sure if I asked you a question.
Yeah, I understand the motivation, but I personally don't think the choice bound is something new in that sense because ASP has such feature.
I mean, okay.
We can discuss later if you are interested.
All right. Let's thank Ilyas and all the speakers who gave excellent talks in this session and the audience for asking great questions. Thank you.
eBPF programs more secure?
Yeah, so I'm Lucas Avalia, and I will be giving I will be giving this talk on verifying eBPF programs using this lovely type system. This is joint work between Florida State University, the University of Waterloo, and Certora Incorporated. So we have a lot of material to get through. So what is eBPF? eBPF is a system for hot loading kernel extensions into a running operating system. This is commonly used for things like packet filtering, process monitoring, security auditing, and many other uses. And this is also used throughout industry. This is not merely just academic code. So here's some companies that use this technology. So you may be thinking to yourself, wait a minute, if we're hot loading kernel extensions into a running operating system, that's not safe at all. You know, we could compromise the kernel in some way, we could crash the whole operating system. You know, lots of other bad stuff can happen like that. And so what we require, or what eBPF requires, is that all programs must be formally verified. And what we mean by formally verified here is that it has to meet certain minimal safety criteria in order to run in the kernel. So we're not interested in, say, a general verification of arbitrary properties, but just some very specific ones for kernel safety. Now, eBPF programs do have some restrictions that can make this much easier. Like, for example, they do not allocate memory while they're running. All the memory that they have is fixed at compile time. That being said, so the general architecture here is as follows. So we have our eBPF program here in user space, and then in kernel space we have a verifier. And when we want to load an eBPF program into kernel space, we have to give it to the verifier. If the verifier is not happy, we have to modify our program. But if the verifier is happy, then we can just compile it using a just-in-time compiler and execute it, and we may get some output that is visible from user space. So this is a general workflow of how eBPF works. So let's talk more about what we mean by minimal eBPF safety. So there's two properties that we're especially interested in here. One is called information flow safety, which is basically that an eBPF program never exposes any kind of kernel secrets, such as any information about the address space, to the user. And that two, eBPF programs must be memory safe. This means that an eBPF program can only access certain memory regions and never goes outside of these bounds. So here's a very small 7-line eBPF program. Here we get this parameter called the context, which is passed to the program from the operating system. Now what the context looks like depends on where the program is attached, but for this example, it's on the network stack somewhere, so we can do things like load a pointer to the beginning of a packet, which we do on line 1, and then on line 2, we load the end of the packet into a variable. And then we check here on line 3 if somehow data was greater than data end, which means something went catastrophically wrong and we have to exit. Otherwise, we're going to try to load and store 4 bytes on line 4. But you may be thinking to yourself, wait a minute, that's not safe. And the reason why comes down to line 3, because we could get in this awkward situation where data equals end, in which case we just don't have 4 bytes to load or store. So what we would do in this context is add this extra piece, data plus size of int. This guarantees that we do in fact have at least 4 bytes of memory to load and store. So we take this lovely program and we want to shove it into one of these verifiers, and we get this lovely log. And we have to like read through all of this, and after 130 lines of reading through this verifier log, we find out actually there's something is wrong with how we've read and write to this packet region. So with that being said, let's talk about some existing verifiers. So the first is called the Linux verifier. As its name implies, it runs on Linux, and it uses symbolic execution to analyze programs. It, like I said, was the very first eBPF verifier created. And the second verifier that we're interested in is called Prevail. It uses abstract interpretation, and this is part of the eBPF for Windows project. But one of the things that we've observed is that, you know, we have 2 different verifiers, but some of the same problems emerge. These verifiers are monolithic, they live entirely in kernel space, and the users are not capable of providing guidance because you would have to cross that boundary from user space into kernel space. And generally, as we've seen, these logs are hard to read. So what we believe is that these are fundamentally architecture problems, And what we propose is a type-based system that addresses some of these architectural problems. So what we can do with a type system is do type inference in user space. This gives us a proof certificate that the eBPF program is safe. And then we can do type checking in kernel space. And we also believe generally that types are more intuitive for programmers. You know, it's easier for programmers to think in terms of types rather than in verifier logs. So the architecture we're proposing now is we start with our user space and kernel space distinction, and we have our eBPF program. We pass it to a type inference engine to analyze it. From there, we have a set of annotated instructions that we try to pass it off to the type checker. If the type checker is not happy, then we can modify our annotations. But if the type checker is satisfied, then we compile it, execute it, and we get our output. So let's talk about some of our basic types. We have three kinds of objects that we're interested in analyzing: pointers, numbers, and file descriptors. So now I'm going to show you our type lattice to make this kind of easy to visualize. We have the top type, any, and then underneath of it we have pointer, number, and map file descriptor. Now pointers, we also have to consider their provenance. So we have different kinds of pointers: stack, context, packet, and shared. These shared pointers are related to maps. And then finally, we have the bottom type, which kind of represents an erroneous computation. And so the reason why we're concerned with the provenance of pointers is because of information flow safety. So for example, we're not allowed to store another pointer into the shared region or to the packet region. The reason for this is we may have now exposed a secret to the user. On the other hand, it's totally fine to do this for the stack region because the compiler might do something like register spilling. And so we actually do have to consider different semantics for different pointer types. But we don't just have these basic types. We also have flow sensitivity and type refinements. So to talk about these, we need to talk a little bit about how our type environments look like. So we have gamma, which is a mapping of registers to types. And we have delta, which is an abstraction of the memory regions. And we do two basic type judgments. We can say that from gamma and delta, we can judge that an expression has a certain type tau. And we can also say that from gamma and delta, we can prove that a certain instruction gives us a new gamma prime and delta prime. So the second judgment here is what we mean by flow sensitivity. And the state of delta and gamma depend on the location in the program. We also have type refinements. So this is the general notation we use for that. Here in the left compartment, we have what we call the value variable. And then here in the right compartment, we have some refinement predicate that constrains this value variable in some way. So for example, I have our initial gamma and delta, and then we encounter this instruction where we assign R1 the number 12. And what we should get as the resulting state is now R1 is mapping to a new singleton type. Similarly, if we have a load or store instruction, we start out with this precondition where R10 is pointing to the stack and it has offset 512. And then if we want to store something at address 508, say the number 12, then we can update delta with that corresponding type at that corresponding address and at that corresponding region label. So this is basically how flow sensitivity and type refinement works. And for most regions, this is all we really need to do. We don't really need much more complicated type refinements. However, when we get to handling packet pointers, this gets to be more complicated. So the size of the packet pointer is not known at compile time, which is unfortunate. So we have to make sure that the program has certain runtime checks that keep us within the bounds of the packet region. And so for that, we have to use more complex type refinements, and we use some special symbols for that: meta, begin, and end, which point to the metadata, the beginning, and the end of the packet region naturally. And we hold this invariant that there's a sort of ordering on these special symbols. And we also use these other structures called slack variables, which are used to keep track of these previous runtime checks from previous basic blocks. And we want to basically delay the analysis of these runtime checks as much as possible. So this is an example of what one of our packet pointer types might look like. So this tells us where the the location of where the pointer is pointing to. We have some constraints on our slack variable saying where that slack variable is allowed to live. And then we also have this safety condition, which basically says that we're safe to read up to 8 bytes from the beginning. So let's go back to our example here. We first analyze this and we see that data has type packet and it's pointing to the beginning. Data end is pointing to the end naturally. So here on line 3, something goes catastrophically wrong and data has type none. Now here, we actually now can add on this extra safety condition that begin is less than or equal to end, but we're still not safe yet. When we modify it, we actually now modify the type, and we get begin plus 4 is less than or equal to end, and that's safe to run. So we do type inference in the following way. We traverse the control flow graph, and for one basic block, we join with predecessors, if there are any, and then we infer the types for every instruction in that basic block. Now, if the basic block is the head of a loop, we're going to do the same thing, but we also do this extra widening step, and we're going to kind of repeat this until either a fixed pointer is reached or we just kind of give up and we assume something generic. Okay, so we actually implemented our type inference algorithm in a tool called vrefine. This is implemented as an abstract domain in the Prevail framework, so we took some code from Prevail and we used that to make our type system. And we evaluated this on 420 industrial and synthetic benchmarks. So some of our industrial benchmarks, Cilium, Suricata, OVS, Falco. I'm sorry I don't have references for those. So this is our data here. So it may look like we're solving more benchmarks, but this is actually due to parsing. In reality, our analysis is less precise than what Prevail does, but it's still sufficiently precise. And as a result of that lack of precision, we actually get much better runtimes. So in summary, we've presented a type system for verifying eBPF programs. We've enhanced the debuggability through the use of types. We've improved the modularity of eBPF verification, and we've improved performance as a result. So for future work, we would like to implement our type checker and maybe add termination analysis. So our code is available here, and that's the end of my talk.
All right, questions? So I have a, yeah, go ahead, line up, yeah, please line up, yeah.
Thanks for a nice talk. So I think your system supports a general strong update.
Yes,
yeah.
We do support strong updates.
Yeah, then I'm wondering how you can address the aliasing. I think the aliasing is problematic if your system supports a strong update.
Yeah, so aliasing is kind of difficult, and we do actually support it, yes. And so the way it would work is like if you have an alias, then we can do a type like an assignment instruction, and then we can kind of copy the type from one pointer to another. But we also have an extra rule for propagation, so we can share information between types. Okay. There's a whole heuristic for this. You'll have to look at the paper.
So you track the aliasing information in the type system.
What?
Your type system also tracks the aliasing information. Okay, I see. Thanks.
Hello, I have one question about the semantics. So basically, okay, so you are based on the previous PLDI paper, and I'm interested in the atomic instruction. How can you deal with the atomic instruction, and what's the memory you used, memory model you used?
As for atomic instructions, I'm not really sure how that's implemented personally, so I can't really answer that question.
Okay. But you do support the atomic instruction for your domain?
I'm not sure.
Okay, thanks.
Yeah. All right. Thank you. All right, let's get ready for the second talk. From the unplug and plug it again. You have to play your slides now, yeah. All right. For the second talk, Vimla is going to tell us about how to verify replication-aware linearizability.
Good evening, everyone. I am Bimala, a PhD student at IIT Madras. Today, I will be presenting our work on automatically verifying replication-aware linearizability. This is a joint work with Karthik Nagar, Asim Rastogi, and K.C. Sivaramakrishnan. So, modern cloud-based software services replicate data across multiple geographically distributed locations to improve fault tolerance, reduce latency, and ensure availability. This is especially important in collaborative tools like Google Docs when multiple users can concurrently edit the same document. These services rely on centralized servers to resolve conflicts and to maintain consistency across replicas. However, there is a growing shift towards decentralized systems seen in platforms like GitHub. Here, each user has a full copy of data and changes are synchronized peer-to-peer. This local first model brings in benefits like better security, privacy, and user ownership of data. But how do we build systems like this? The answer is to embed replication into the data type. We designed the system from the ground up to support multiple divergent copies that can be merged later. Recently, mergeable replicated data types or MRDTs have emerged as a systematic approach to embed replication into the data types. So, any sequential data type with a three-way merge function becomes an MRDT. So, this three-way merge function is a ternary function that takes as input the two versions that needs to be merged and the lowest common ancestor, which is the most recent version from which the two versions diverged. This function is used to reconcile the divergent states that has occurred at multiple replicas. For example, let us take an example of an add-win set MRDT. So, this MRDT supports three operations, that is, you can add an element to the set, remove an element from the set, and read the set. The three-way merge function for this MRDT is given here. So, it takes as input the LCA and the two version that needs to be merged, and it computes the union of the intersection of the elements at the LCA and the two versions. So, this is basically this set contains the unchanged elements, that is the elements that were not deleted and unmodified. And then this V1 minus LCA and V2 minus LCA are the newly added elements to the set. So, this is how we implement the three-way merge function. So, let us take one example. For instance, let us take that there is one replica that starts with an empty set, and then we fork off replica 2 from this replica 1, and then we apply two operations, add operations. So, replica 1 adds A to the set with the timestamp 1, and replica 2 adds B with timestamp 2. So, the states becomes A, 1 and B, 2, and now when replica 2 merges with 1, the resultant set contains A and B. But are we sure that this merge function is correct, and if so, how do we automatically verify it? So, given an implementation of MRDT, we need a way to define the expected behavior, so we can check whether an implementation conforms to the expected behavior. A natural way to specify this behavior is by explaining the outcome of the concurrent execution in terms of linearization. That is sequential ordering of operations that are consistent with what the replica has observed. So, given an execution graph like this, the key question is, can we prove that the state sigma 7 and sigma 8 are same as the state we would get by applying a valid linearization of operations seen by the replica from the starting state? So, replication-aware linearizability is a correctness criterion used in CRDTs. So, the main idea here is that it requires all replicas to have a state which can be obtained by linearizing the update operations visible to the replica according to the sequential specification, and this linearization must respect the visibility relation, but there is no need for real-time constraints unlike classical linearizability. So, in our work NEEM, we adapt RA linearizability to the MRDT system model and introduce a simple specification framework based on conflict resolution policies of concurrent update operations. Then we propose a sound verification technique for proving the RA linearizability. At the core of this is a technique called bottom-up linearization, which uses some simple algebraic properties of merge function to show that it produces a valid linearization. We then design an induction scheme to automatically verify the required algebraic properties and generate a set of verification conditions and prove it in the F-star programming language. So, first let us see what an MRDT developer has to provide to our framework. So, a developer has to provide an MRDT implementation, which is the MRDT state, the set of supported operations, and the three-way merge function. And the important thing to note is that not all operations commute with each other. For example, in the add-win set that we saw earlier, the add and the remove operations of the same element does not commute with each other. So, while generating the linearization, we need a deterministic way to resolve the conflicts. So, if these operations have to occur sequentially, in what order they would occur. So, in the case of add-win semantics, the conflict resolution policy ensures that the remove comes before the add of the same element to preserve the advent semantics. So given an MRDT implementation in the conflict resolution policy, let's see how we prove array linearizability. The proof is straightforward if there is only a single replica where all update operation happens because there is no interleaving of operations. The complexity arises when updates occur concurrently at multiple replicas, and the key challenge now is to show that the merge function produces a state that corresponds to the valid linearization of update operation that are seen by both the replicas. To address this, we introduce a technique called bottom-up linearization, which uses some simple algebraic properties to produce the correct linearization. So the 5 rules given on the right hand side are used to construct the linearization of operations. The core idea is to identify one event, apply to the argument of the merge on the left hand side of the consequent, extract that event out by removing it from the argument, and instead apply it to the result of the merge. And the premises of this rule specify the condition under which this extraction needs to be done. So let's walk through how we build the linearization for the sample execution. So here event E1 and E2 are 2 local conflicting events, and according to the conflict resolution policy, E1 should be ordered before E2. So we apply the bottom up 2-op rule and we peel off E2 from the argument, and now we have to prove this. Now only E1 remains on replica 1, and then now we can apply the bottom up 1-op rule and then peel off event E1. Now only LCA events remain, and now we can apply the merge idempotence to obtain the correct linearization. While we have identified sufficient conditions to show array linearizability, proving these conditions for arbitrary MRDTs is not straightforward, because the rules that I showed earlier has universal quantification on the MRDT states. We need to show these properties only for feasible states that might arise during an actual execution. To make this more concrete, consider the same execution except that the state at the LCA contains a, 2. So if the replica 2 attempts to add the element a with the same timestamp, we get the same state. The linearization order remains the same as that of the previous example, but if you see that the left hand side is not equal to the right hand side. This scenario occurs because if the LCA had the tuple a, 2, there must have been an add event that added the element a with timestamp 2. And now the replica 2 cannot add another event with the same timestamp, as timestamps are unique across all events. But such arguments are hard to infer and would change across different MRDTs. So these the values of this L, A and B are not feasible in actual execution, but we need to consider only feasible states for proving. So now we characterize these feasible states by sequence of MRDT update operations, and we do induction on these sequences to establish this property. How do we apply this induction? So the merge function takes 3 inputs, sigma t and sigma 1 and sigma 2, and this pi t is the sequence of event that applied on the initial state gives the state of the LCA. So we apply the induction on this sequence pi t, and the base case, so we have this base case and the inductive case. So base case is easy to prove because it contains only the sigma naught, which is the initial state, which is an empty set, and it is easy to prove the property. For the inductive case, we assume that the property holds for some LCA state sigma t, and we aim to prove that this property still holds even after applying one more update event. This step can be automatically verified using the fact that the events E1, E2 and E3 all have different timestamps, and the inductive hypothesis helps us to prove the consequent. So this proves this completes the proof of bottom-up 2-op rule. A similar inductive argument is used to prove the properties about the feasible state sigma 1 and sigma 2 also. So finally, we prove a theorem that states that any MRDT that satisfies the required algebraic properties are array linearizable. And we also show that if an MRDT is array linearizable, then the query results match what we would have got by applying the linearization of update operation visible to that query operation when applied to the initial state. So we have implemented our verification technique in the FSTAR programming language, and we have verified several MRDTs. And our FSTAR framework includes an interface that defines the required signature for the MRDT implementation, and the VZs are encoded as FSTAR lemmas. And all that the MRDT developer has to do is that he has to provide he has to implement the MRDT code and use FSTAR to prove these lemmas. Once these lemmas are proven, our meta theory guarantees that the MRDT is array linearizable. So some of the MRDTs we verified are from the previous work or translations of known MRDTs. We have also created some new MRDT, verified new MRDT implementation that are marked with a star. And the second column in the table gives the conflict resolution policies we have used for the MRDTs, and this column gives the lines of code. The last column shows the verification time. During verification, we also found bugs in the earlier verified implementation, which we fixed in our work. So NEEM also supports verification of state-based CRDTs. And our code is available in this following GitHub repo. Yeah, thank you.
So next speaker, come forward to get yourself wired up while we line for questions. Yes.
Two questions. Did you experience any difference when verifying with your method, your approach, MRDTs and state-based CRDTs, because they come with some more guarantees?
Yeah. So MRDT is a kind of state-based CRDT. So in state-based CRDT, since it follows a lattice model, so we need to prove only the 3 properties like associativity, idempotence, and commutativity. But MRDT system model is much more complex because it contains the least common ancestor, and more complexities arises when there are intermediate merges and also it's like bit more difficult.
And any comparison to other work that has the goal of verifying CRDTs? Maybe this is more focused on CRDTs and yours is broader scope with MRDTs, am I right?
Focus on the previous work is, there are other verification work in MRDTs that uses declarative specification which are not automated, like it requires manual proof effort. So in our work we have made the entire verification process automated. So the developer need not do any extra effort to verify their implementations.
We have time for more questions. So can you go to the previous slide briefly? So when you say you verify implementation, you meant you re-implement in F star, verify in F star.
Implement it in the F star. The implementation itself is in the F star programming language, and the VZs are also encoded in the F star.
So the real implementation could be in a different language.
Yeah, so we can extract the OCaml code out of the verified implementation and use it in distributed systems. Like.
So now you have this anybody else? So you have this RC policy.
Yeah.
So how did this impact your verification time or make the verification harder or easier?
So this RC policy are like MRDT specific, like you define based on the semantics of the data type, you define the RC policy. And the verification time is not based on the RC policy, it basically depends on the complexity of the implementation. So I don't think it depends on the RC policy, but on the how complex the implementation is. If it is a complex implementation, its verification time is large.
So for inductive proofs, that's also done automatically. You don't need to put in any inductive invariants.
No inductive. Everything is taken care by the meta theory, and we have a set of VCs that are generated, which are automatically verified in F star.
So the third talk is about the impact of formal verification on software development. Eric is giving the talk.
So hi everyone, I'm Eric, and today I'm going to talk about the impact of formal verification on software development. And this is the work I've done with my collaborator, IUCSD. So when I talk about formal verification, I'm going to focus on automated verification or auto-active verification, which is basically you write your code and you're going to write like pre and post conditions, so what should all that entry and exit of your function, and then this is going to get transformed by the verifier, and then send to a SMT solver that is going to tell you sad or unsad. And why I'm talking about this is because this is actually here, like in academia, but also in industry, and this is getting deployed with critical systems such as like operating system or authorization protocol. And so why can we explain that like this thing is actually getting adopted? I would say two things. The first thing is like solvers are better than ever, and now also we have actually maintained verifiers that are actually used by industry. And so this is great, but yet automated verification is far from mainstream. And when you read the literature, you'll mainly see two things. The first thing being like, oh, well, there's still a huge amount of effort, and you'll often see at least this ratio of like 5 to 1, meaning 5 lines of proof annotation versus 1 line of code. And the second thing is the expertise. You need to be a formal method expert to actually use verification. And I want to come back on this because that's kind of what we hear, but it is a claim that is maybe not entirely true. And I think there's different kind of expertise. Yes, there's on one side the formal method wizard that will tell you like soundness is all I want to hear, I care about completeness and all these things, but there's also like another kind of expert, which is the hardcore programmer that would tell you like, what about the buzz factor? And this is a quote that I got from my study, which is basically what happened to this tool if the person that maintains it get actually hit by a bus? Who is going to take care of it? And this is something that they care about. So really different things that they care about when they actually write code, right? But one thing that they care, both of them, is they want the code to work. And actually, now with this kind of tools, automated verifiers, such as the one I'm going to focus on today, Daphne, both of these experts actually try to verify the code. So today, I'm going to try to give you like some experience on Daphne, but I hope that this is also applicable to other kind of tool, or even like if you're trying to design your own tool for formal verification. And so again, I want to focus on these experts. And for this, I want to take this user-centric approach and understand, okay, these people are writing software and then trying to verify them with Daphne. So my question as a user study is like, what happened to software development now when you add formal verification? And so for this, I use a technique from social science called grounded theory, where we start by questions that we ask during sort of like semi-structured interviews. And then it ends up in a recording that is like around an hour long. We get a transcript, we try to annotate the transcript and analyze it. And from this analysis, we identify patterns and we refine the question and we iterate again and again until we kind of arrive to stable points where the patterns are the same. And so who did we ask this question to? Well, we had 14 participants, and we were really lucky because we had both these formal method wizards, but also this really experienced engineer. And we had an average of like 5 years of experience in the industry, with some of them being like actually in the industry since more than 10 years. And a wide range of domain for formal verification. And so what kind of question did we ask? Well, we went through all the stage of the development. The one we think about at first is which is like designing and building with like the specification, the proof, and the one that sometimes we tend to forget when we actually try to verify software, which is more like code review, testing, maintenance, what happened to my code after. And so what we do ask is like, okay, how do you go about specifying your code? Or like, what happened in your code once it is deployed? So these kind of questions. And so today, I'm going to try to give you a glimpse of some of the results that we discover by talking to people, to these users, and then trying to analyze the patterns. And so I want to come back to like, compared to regular programming, how does it differ or how is it sometimes similar? And so I'm going to talk about 3 things. For proof debugging, unlike normal debugging, it happens mostly in your head. There's no print in formal verification. And the second thing is proof hardening, which is similar to, I would say, a program where like a good proof is actually a simple proof to some extent. Meaning that in the same way you would, like if you have a big function in your program and you're going to try to like make it smaller and like make it into multiple function, you would do the same for proofs. And the last one is code reviews, where like definitely spec, proof, and code is an information overload, and we need to rethink that. And so for the first one, for proof debugging, this is an example that I got from my user study where they basically try to this method where they're really simple. They try to apply a discount on X with a certain percentage, and they have this precondition that is like, okay, X needs to be positive, and the percentage needs to be a correct percentage as a discount, and we want to show that the result is indeed positive. And so you can see the implementation here. It's quite straightforward, and what's happening when you try to verify this code in Daphne is you get an error message saying like cannot prove that the result is actually positive. And so when we ask the user, how do you react about these things, like what do you ask yourself, they will tell you like, okay, in this case, I'm asking myself like, who's wrong, me or Daphne? Meaning like, is the program or the specification that I wrote wrong, or is it actually Daphne that is not able to prove this? And so how do they go about, so here they kind of rapidly rule out the I'm wrong, and they like try to understand why Daphne cannot prove this. And so how do you go about that? Well, the same way you do for programming, you would try to interpret the error message. And so let's see what the user reports when they read the error message. Well, right now, the thing just cannot tell you that 0.1 times 0.1 is greater than 0, which is quite like horrible. And they will think that this thing is kind of calling on an LM, but the thing is supposed to be good at math, and you have to give a better error message. And this is from like a hardcore engineer. They get really frustrated really fast about tool giving you this kind of answers. So okay, interpreting the error message didn't go so well. So what's the next solution? Because we cannot stay there, otherwise we cannot verify anything. The second thing is the sort of like active debugging, which they debug via assertion as breakpoints. And so here, what they're going to try to add is, for example, these assertions to kind of guide the solver through to help the solver answer to prove that result is positive. And so here they try to add this assertion, but sadly, this is not enough. This is not what the solver needs. Indeed, and the challenge here is you need to actually build a mental model of the implicit verifier state. So what does the verifier knows, what does SMT know, and what it is able to infer. And what's needed here is that to say that the multiplication of two positive numbers is actually positive. And so as a sort of recommendation as a community, I think if we think about this kind of tool, we need to definitely kind of explicate this verifier state and define and visualize what the context is, especially if we're asking to a solver that is able to come up with more facts. So that's for proof debugging. So now we have the proof that worked at least once. Let's see if we can make it prove all the time. And you would ask yourself why? Well, because there's this problem of brittle proof. And so a brittle proof is a proof that previously verified, but where trivial unrelated change can cause the proof to fail. And this is because like the SMT solver is at the edge of what it can actually solve, and now you change the name of a variable and the proof fail. And so the reaction of the users is quite a lot of frustration. One of the things they would say is like there's something soul crushing about having to go back to things that you thought were done and do them again. But okay, so like let's try to understand what's the problem so we can actually fix it and make the proof robust, right? And so the main thing that a user report is the problem is the context. For the record, like in one of the projects, the amount of SMT queries that was sent to the solver was around 5 gigabytes. So I let you imagine the number of characters that 5 gigabytes represent, right? And on top of this, like this context gets blown up by quantifiers, but also like there's a ton of like visibility of the certain facts that shouldn't be included. And finally, in Daphne, like there's specifically this memory model with frame condition that can blow up your context. Okay, so now we have the problem, but the good news is there's actually a solution to this. And when we ask to developers, what they tell you is like, yeah, at first I had this problem, but now I think I can actually overcome it because it mainly requires discipline. And so what do they mean by this? Well, this is first a sort of extreme approach. I want Daphne to be as stupid as possible, make me really verbose, but make sure the proofs are easy for Daphne. And so you would think, okay, this seems like we're like back to proof assistant again, so what's the point of using Daphne anyway? Well, there's a sort of like less extreme approach, which is like, okay, if I don't play that game, if I'm in need to give more resources to the SMT solver, I just try to break it down to something that is actually reasonable for the solver. And since we talk about discipline, I think in engineering there's always a way, it's really important to think about a way to enforce this discipline. And so we need to think about like tooling or like ways to like prevent this proof from getting to the roof and have some kind of configurable linters. And finally, I want to talk about the code reviews and show that specification proof and code is information overload. So how does a normal code review happens? So the reviewer sees the code, and like classic reviewer would say like, yeah, looks good to me, it's great, and we're done. Well, here it's completely different. Like we have not only the proof or the code, but we have also the proof, we have the specification, we have also the target code that is actually the one running. And so the reviewer is like, okay, there's so many artifacts, what should I look at? And what I should focus on? And so again, what do the user report? Well, it's kind of a really mixed bag. They care about different things. Some people are telling us like the glorious thing about proof is that they are self-proving. There's no need to look about somebody else's proof. But just before I told you about like proof robustness, so actually people care about, some people care about looking at the proof because they want it to be robust and maintainable. Some other people would tell you like, well, reviews are the only time to check the pre and post condition are strong enough. So this is really the thing I'm focusing on because that's the moment I can check it. And finally, and maybe more surprisingly, some people care about the transpile code, the final artifact. Why? Because they work with other people, simply. And these other people don't formally verify the code. They run like the Java, they run like thing, and so they want the code, for example, to be integrated with theirs, and they also want the code to be performant, and that's dictated by the transpile code. So we should not forget about this. But what we should understand here, and I think that resonates with what I've been said yesterday at the keynote, is we need to have a way to focus on certain part of the code and like let's say we have a specification, I want to look at the code that is linked to the specification and maybe not look at the proof. Or maybe actually I want to focus only on the proof because I want to focus this time on a path for robustness. And so we need to think like what does it mean to toggle this focus while kind of like still keeping this sort of holistic view. And so finally, I want to finish by like I hope I answered some of the question around like what happens to software development when you add formal verification. We were lucky enough to have these 14 experienced developers. We interviewed them with this method from social science, grounded theory, and today I give you a glimpse. I talked about like proof debugging, proof hardening, code reviews, but there's way more in the paper, and feel free to read it. Thank you.
Okay. All right. Questions? Also, next speaker can come get set up.
Hi, great talk. I like this idea of a linter. Did you have any ideas of any specific like lint rules that a hypothetical linter would have?
So, I mean, I guess like for a lot of queries, like for a lot of code now, one example is like the visibility thing. And so you can have like function unrolling and like a lot of like function that get added into your context. And I think it like it would be nice to have like the linter tells you like, okay, this one is visible, and so it's added to your context, but you're actually never using it. So I think that's one thing. I think another thing that has been done a bit is like around unsat core, where it tells you like, okay, these facts are not needed, you can remove them, and so you could have like some linting around this. For now, it's like two different dissociated things. It's like just you run this like feedback with unsat core, but it's not actually in your IDE. So like people are not necessarily using it on the daily.
Yeah. Thank you.
Do you know if similar studies have been conducted for software developers who do not have prior experience with formal verification tools and trying to get them to adopt it, or seeing their reaction to it?
Can you repeat your question, please?
Have studies like this been conducted for examining software developers who do not have prior experience with formal verification?
So actually, in our study, when I talked about this hardcore engineer, some of them had no formal verification experience before, and they used the tool for the first time as like, I mean, my team goal is to verify this code or like to use Daphne, and so I need to get into it. And this is why we have like such reaction on like, why is it not able to like prove that 0.1 times 0.1 is greater than 0?
Thank you.
Here again. You need to extend display. Thank you. All right, next talk, Kinho will tell us about verifying crash consistency.
Hi all. Today I'm going to talk about our paper towards verifying crash consistency. This is a collaborative work with my colleague Konan and our advisor Brian Dembski. Ensuring crash consistency or implementing programs correctly in the presence of crash shows up in various contexts. Here we have two examples. On the left, we have persistent memory, which is a non-volatile memory that can replace traditional DRAM with only about 2 to 3 times higher latency while maintaining the content in the presence of crash. And on the right, we have CXL, a new open standard for pooling memory across the network via cache coherent links between machines, where each machine failure is independent from each other, giving a partial crash model. Even if we use these hardware technologies that survive crashes, either fully or partially, we still face problems when designing crash-consistent data structures. First, in many failure scenarios, CPU cache is volatile, hence proper fence and flush operations are required by the users. If these operations are not specified, those cache flushes are done arbitrarily, which result in stores may not be persisted in the same order as they are executed. Also, even if the persistence order is ensured by the proper fence and flush operations, we still need to design data structure correctly in the presence of crash. We decompose the problem of implementing crash-consistent data structure into 2 parts. First, proper fence and flush insertion, and second, the correct design of the data structure, and our work mainly focuses on the second part. Let's first look at how we define crash consistency. Here's an abstract representation of concurrent program execution, where each line represents threads running operations. We assume partial crash model and say the crashes occur at these points asynchronously. The parts that are not executed due to the crash are indicated by the gray area. Our criteria for the crash consistency is all or nothing semantics, ensuring the atomicity of data structure operations. In other words, operation 2 finished before the crash and operation 3 has not started due to the crash. And we would like to make operations that are interrupted by the crash, operation 1 and 4, for instance, also acts as if they either finished or not started at all. So for instance, if the following execution where operation 1 and 2 are complete, while operation 4 has not started at all, is equivalent to the previous execution, then we say the execution follows all or nothing semantics. One programming paradigm to achieve all or nothing semantics is the idea of commit store, where there is exactly one point in each operation that logically stores the whole operation. If the implementation follows the commit store pattern, it trivially satisfies all or nothing semantics. For instance, if the red lines indicate the commit store points, then in this execution, operation 1 is logically complete, since its commit store is completed before the crash, and operation 4 is logically not started at all, since its commit store is not applied. We wanted to help user to implement crash-consistent data structure following the commit store pattern by providing our language, CrashLang. Here's an overview of how CrashLang works. Users first write CrashLang source code, and if it passes our type system, then the backend compiler inserts proper fence and flush operations with some additional code injection to provide crash consistency, and is finally transpiled to Rust code, and the output code is guaranteed to be crash consistent. As mentioned, we have decomposed the problem into 2 parts, where the type system ensures the correct design of crash consistent data structure, and the fence and flush insertion from the backend compiler ensures the correct persistent order. Let's start with a concrete example to illustrate some CrashLang features. Harris linked list is a lock-free data structure, which turns out to be a great example of showing the commit store pattern. The elements are stored in an ascending order, and the insertion and deletion methods traverse the list and find the correct spot to either insert or delete using compare and swap operation. Before getting into the example, we're noting that CrashLang is built upon the type system called lolcat, which is ensuring linear ownership of references. Hence, our language construct is similar to theirs. Here's an example run of insertion. Say element 2 and 5 already exist in the list with the sentinel nodes at each end, and insert of 4 is called. The insertion starts with allocating a new node and setting up the key. Then it traverses the list to get to the position for the insertion, indicated by the left and right pointers. The next pointer of the new node is set to the right, and the compare and swap on left.next to the new node is applied. If the cast succeeds, it completes the insertion of the new node. In the insertion, there are multiple steps of updating the global state consisting of multiple store operations, and it seems problematic if a crash occurs in the middle of these stores because the partial update of the insertion is applied to the global state, contradicting the all or nothing semantics. However, if a crash occurs before the cast of left.next is done, all previous updates are local to the current thread and invisible to other threads, and those stores will have no effect upon crash. And these stores become visible after the cast on the left.next is performed, which is logically committing the whole insertion operation. Hence, such cast serves as a commit store of the insert operation, and the rest of the stores that are invisible to other threads, we call them physically invisible stores. Our type system distinguishes these physically invisible stores by keeping track of the references that are exclusive to the current thread with the type called pristine. When a new node is created, the reference has a pristine type and keeps its pristineness until the cast of left.next points to it. And when a successful cast exposes the new node to other threads, this is when the new node reference loses its pristineness and becomes visible to other threads. Using this pristine types, any stores on pristine objects are physically invisible stores, and these stores will have no logical effect on a global view. Next is deletion. Again, we start with 2 elements, 2 and 5, and the delete of 5 is called. The correct position is found with the left and right pointers after traversal. Note that naively casting left.next to right.next result in an incorrect implementation, since right.next may be modified during the process. Hence, the deletion of an element is done in 2 steps. We first make sure that the right.next is immutable, then perform the cast that removes the right node. To do so, given a pointer address of right.next, we steal 1 bit from the address and use it as a mark bit, and this bit will be used as a logical indication of the safe cast for deletion. Back to the example, after finding the left and right positions, we first mark the bit atomically using compare and swap, marking the bit and making it immutable, and we say the pointer is fixed. Then the compare and swap is applied, which completes the deletion operation. Similar to the insertion case, we have multiple stores fixing the right.next pointer and cast of left.next. And if a crash occurs between fixing the pointer and the deletion cast, it seems like the implementation doesn't follow the all or nothing semantics, since the deletion is partially completed. The solution is to make such deletion cast to be every thread's duty. As mentioned, fixed pointer is used as a logical indication of a node deletion. Hence, if the current thread crashes before the deletion cast, and say if thread 2 notices this, it will perform this compare and swap instead, which effectively completes the crashed operation. And we say thread 2 helped the operation. In CrashLang, users can specify when and how these helping is done in the struct declaration using help signature, which will be explained in detail in a few slides. Hence, fixing the pointer, which is a logical indication of the deletion, is a commit store. And for the explicit deletion cast, we call it a helping action. CrashLang provides multiple features to support the helping action. First, to manipulate the marked bit of a pointer, CrashLang has 2 primitives, isStable and fix. IsStable checks if the given pointer's marked bit is set, and fix marks the given pointer, making it immutable. Also, we allow users to annotate the fields to indicate when helping actions are necessary and how they are done. In the example, the next pointer in the node struct is annotated with a help type, which we call a helpable field, with an additional field in the angle bracket, which is called a condition field. Whenever a helpable field is accessed, if the corresponding condition field is fixed, a proper helping action of casting the helpable field to the fixed pointer address is generated using these annotation, which ensures helping action is done by any thread observing this condition. We have seen 2 examples of crash-consistent data structure implementation using a commit store pattern. Simply put, in a data structure operation, there is a commit store that logically commits the whole operation, and any other stores must have no logical effects. CrashLang type system identifies 3 kinds of stores that have no logical effects. physically invisible stores, helping action, and logically invisible stores. Logically, we didn't include the details of logically invisible stores due to a limited time, and it can be found in the main paper. We have implemented multiple data structures on crash slang: stack, queue, linked list, binary search tree, and hash table. First, although we have a crash consistency proof, we empirically check the crash consistency of crash slang data structure implementations. For each data structure, we first ran a concurrent execution of threads non-deterministically and injected partial crashes between every possible store operations with around 10,000 to 10 million elements. And as expected, our generated code has no crash consistency bugs. We also compared the performance of our data structure implementation with the handwritten versions and the benchmarks from Memento, where Memento is a type system with a user annotation guaranteeing crash consistency, which is similar to our approach. For each benchmark, we had multiple experiments with different numbers of threads and adjusting the ratio of operations. For each graph, x-axis represents a different number of threads, and y-axis represents the time to finish operations. Simply put, lower time means better performance. Blue, orange, green bars represent CrashLang, handwritten, and Memento, respectively. And as mentioned, we varied the ratio of operations for each experiment, and we are presenting one for each since different ratio of operations didn't change the graph drastically. Overall, CrashLang is slightly slower than the handwritten version for all three cases, and for the comparison with Memento for stack and queue, CrashLang is faster on average and significantly faster for linked list. We constructed CrashLang and its type system to help users implementing crash-consistent data structure using commit store pattern, and we proved that the data structure implementation is crash-consistent. We have implemented various crash-consistent data structures to show the usability of our language and evaluated the correctness and performance as well. There are more language supports in CrashLang that are not presented in this talk, and you can find more detail in our main paper, including more features and formalisms with the proof. That's all I have for today. Thank you.
Speaker. All right. So your next speaker. All right. So you can set up, and while people are thinking of questions. Oh yeah, sure. Go ahead. Yeah.
Sorry, real quick before I get mic'd. I noticed the techniques you're also. Hi, I'm Finn from UBC. I noticed the techniques you're showing and like the semantics are very similar to things I've seen people use in the multi-core, like high-performance data structures community. It's not anything to do with crash consistency, but a lot of other lock-free synchronization, work stealing, etc. mechanisms. Would your work be applicable to this or related to it in some way?
Let's see. I know there are some lock-free data structure implementations that follows this commit store pattern. So yes, I believe if the implementation falls into this commit store pattern, then of course, yeah.
Thanks for the very nice talk. I was wondering, you generate Rust code in the end after you've used your type system. I wondered have you thought about, would there be some way that you could provide annotations on Rust code directly? So adapt your system to be able to integrate in some way with the type system that's already in Rust?
Yes, that was actually one of our reviewers' comment that, and yes, of course, we were also thinking to just implement this idea as like the additional type checker in Rust. Yeah.
Cool. Thanks.
Yeah.
I think we should swap the laptop. Yeah. Maybe as you're swapping. So for the helper function, what if the helper also crash? Does it, like, how do you make sure the helper's crash does not influence the rest of the behavior?
What do you mean?
So you have helper thread come back to finish the job, right? If it crash again, how do your proof apply to this scenario? It is offline now that.
Yeah, we can talk about it later. Thank you.
All right, so next talk. So Finn will tell us about linking implementation with their verified designs.
All right, thank you for your introduction. So let's talk about trace validation.
first of all, just to set our basics, distributed systems are well known to be really confusing to deal with. Concurrency makes sure you don't know quite what order things happened in. Partial failure makes sure that you're not sure how much of your system might necessarily be running. And network semantics make sure that you're not quite sure when or how many of any given message gets received. TLA Plus is one of quite a few ways of trying to cope with all of this confusion. How does it help exactly? Well, it's an abstract modeling tool, and it allows you to describe your system as a kind of set theoretic state machine kind of description with various high-level mathematical abstractions, which you can then model check and verify against properties to see if it does what you think. It's had some degree of adoption in industrial projects, and some big systems have specifications in it. But there's no real link to their actual implementations, which are usually carefully engineered, C++, Java, or something, but not particularly related to your TLA Plus specification at all. One way to deal with this lack of relationship, which can obviously lead to all sorts of desynchronizations, is trace validation, which is a TLA Plus land technique that has had some degree of development over the last few years and some industrial successes. What is it? It's a way of taking logs from running your handwritten implementation and describing a formal relationship between events in the logs and what your specification actually says in terms of state variables and actions. And then you can use a model checker to resolve the ambiguities in information that is not in the log, ambiguities in the formal relationship you describe between log and specification, and ambiguities in the specification, all of which you can tolerate to some extent by using a model checker to solve for those things. Now, this is just the state of the art. That's already a thing that you can do. But all of this existing work uses manual setup and instrumentation. So you have to go in and actually add all the logs to your system. You have to write this relationship by hand also. It may be relatively boilerplatey, but you have to do it. And that's, like, fine, but can we do better? Well, in this strange circumstance we have, where we are authors of Pigo, a specification compiler that goes from TLA Plus compatible specifications to generated implementations, we own the entire compilation process and can therefore add much more precise and detailed instrumentation than would normally be reasonable. And we can do all of this automatically while preserving all of these relationships and generating all the stuff. So essentially what we've done is we've automated the process of trace validation for our specification compiler. Here is its architecture diagram, and essentially what we have is modular pluscal, which is our addition to, it's a TLA Plus compatible modeling language, which you can then extract TLA Plus from and generate into Go programs that will then run. What we added to it to make TraceLink, which is our project, is all of this. So we have Go instrumentation, which inserts itself into the implementation code and records a very detailed trace of what happened. And then we have the TraceLink process, which takes the trace and metadata from the specification to generate a complete relationship mapping the trace onto the formal specification, which we may then model check using an out-of-the-box model checker for TLA Plus. And you might think I'm about to tell you how all the Pigo instrumentation and all that works, but actually I won't. I'm going to talk to you about a very specific and interesting detail of how we get to do trace validation that is different from all other trace validation because of the high detail instrumentation we have access to. So let's talk about this trace validation variation. First, I'll tell you about a really, really simple distributed system just for illustration purposes. Imagine we have a global variable x, which is accessed by Alice and Bob. Alice and Bob may increment x. Very exciting operation, I know. To share x, Alice and Bob will exchange UDP messages. And of course, global variable x being shared is a complete lie. Alice and Bob have local copies of x, and it's up to them to keep them in sync correctly. That's why this is a very slightly interesting distributed system. Now, what I want to get at here is, in all prior work on trace validation, what they're validating is a pre-sorted trace. So what we mean by this is we take the log of all the nodes of your system, merge it, sort by timestamp, and we have a complete global order of everything we think happened. Now let me show you an example of something that could result from this. So we have our initial value of x, which is 0, and then Alice increments from 0 to 1. Then Alice sends a copy of x to Bob. Alice increments x from 1 to 2. Bob increments x from 2 to 3. I know some of you might have just noticed something very strange here. And then Bob receives x from Alice. Now, you might think, okay, this is obviously wrong. There's like, that's the wrong way around. But let's take a step back and think about what kind of formal specification we might be validating against. And I will introduce my one little contrived example here. So the spec we're using is x may always increment by 1. X does not go down. And we just view x as a global here. And also, Alice sends x to Bob. This is the actual specification of what is allowed to happen. But in this example, Bob is clearly psychic and has seen something that Bob is not supposed to see. So what's the deal here? Technically, this would be accepted by this slightly lax specification. And for the TLA Plus experts, there's a little small print at the bottom, but basically, trust me that this is a real omission you can make in TLA Plus. You can do all sorts of abstractions and simplifications about things you don't want to talk about, and you might accidentally omit something like the causal relationship between synchronizing x and actually incrementing it so that you would actually accept this entire series of events. Okay, that's kind of annoying and unsatisfying. What could we possibly do about it? Well, remember I was talking about pre-sorted traces. We get to instrument our system using vector clocks and store causal traces instead. So I'm not going to explain what vector clocks are, but understand that formally this gives us a partial order that actually maps causally who exchanged what information at what time. And as a result, we can recreate our trace, but now with a bit of a partial order flair. So Alice has incremented from 0 to 1. Alice sends x to Bob. Alice increments from 1 to 2. And actually, at any point, Bob could have incremented from 2 to 3. That seems a lot more problematic now, even with our very lax standards. And also, Bob can receive x from Alex after Alice sent it. OK, cool. And now we can see the deeply problematic nature of my original example, now that you can actually see the causal traces rather than just a sorted example of it. And this is something we'd be able to detect even without changing anything about our specification. So just to get into this, when you're dealing with causality, you can have multiple interpretations of your trace. Here are some of them. This one, Bob was considered to have incremented x before Alice incremented it, and that's a validation failure. Here's another one that just permutes a couple of them, but is still obviously a validation failure. And here's our original example, which is still possible. So we want to not actually only validate this last one, because if we validate that, if we just like pick this trace, then we still pass it, and we don't want to pass this because there's something obviously very wrong with this system. This gets into the practicalities of actually model checking these things, because we say we have a model checker to solve ambiguities. We are now solving ambiguities of which trace to choose. And we basically get depth-first search, so we pick any one path, roughly speaking, or breadth-first search, pick all the paths. And I don't want to check every path. So we tried doing this, and on one single example, we had to kill the process after 12 hours. It does not work. So we seem to be stuck with one path, but that's completely impractical. So we have this strategy called sidestep, which is essentially we pick one path, and imagine we do get unlucky and we pick the path that would have validated. But for every step of the path, we validate the alternative schedule by one step only. So for every alternative path each step, just one point of it. And what this gives us is a complexity, give or take a constant factor, comparable to single path, which means when we run it, it doesn't take all day. It takes a few minutes. And here, bonus, we can actually find that Bob's incorrect increment is visible even in the initial state. So we can get a really short counterexample to our model checking. Of course, as long as it's findable in one step. This is not a perfect technique, but it's better than all day versus get unlucky even in this case. So there are a lot of other details in our paper that you can check out. And for example, there's how PIGO is instrumented. There's the complete formal semantics of our translation. There's 9 bugs that I will try to talk about maybe one of. And there's a compression scheme for our germinated TLA+, which is normally very big. So our evaluation of this technique and automation process focuses on 3 systems built with PIGO because we rely on the PIGO compiler to do all of our instrumentation. The main one of interest is called Raft KVS, which is a Raft-based key value store. It's a pretty complex system which was built for performance benchmarking and stuff, so it has a lot of fun tricks and is representative relatively of real software. We got log sizes of up to 100,000 events across 26 processes, and some of our counterexamples were over 10,000 states deep. A rough list of the bugs that we found are in some interesting categories. There were wrong specification assumptions, there was one miscompilation in PIGO, and various mismatches in terms of modeling trade-offs. I will tell you a tiny bit about one of them, because that's all I have time for. And that was when we accidentally modeled TCP incorrectly. Essentially, it's not that we did anything strictly wrong in terms of what TCP allows, but rather we over-strengthened its sequencing properties such that we required all TCP connections to the same recipient to be globally sequenced to each other. Again, this is just a little thing where you omit something in TLA+, and you have a very strange counterintuitive consequence come out of it. And we were able to detect this, catch it, triage it, etc., using TraceLink. The other thing that we evaluated was the effectiveness of sidestep. And I won't get into it too much, but it turns out it doesn't change the ability to find bugs very much, but it changes the length of our allowed counterexamples by a great deal. So, for example, it decreased the counterexample length by 11,000 states. Now remember, a human has to actually read and review these states in some way, even with Control F. So I'm very happy that it makes these a lot shorter. It helps immensely with triage. And sometimes it makes your model checking a lot faster as well. In summary, that's basically all I had time to tell you about. We have a push-button validation system for PIGO. Feel free to ask me for details. We have this causal-aware validation and sidestep technique, which I think is interesting and I've spent most of my time telling you about. We found 9 bugs in the PIGO context, and you're welcome to ask me more about those. Our ongoing work is about trying to reduce the reliance on PIGO and apply to other systems, especially applying this causal validation techniques to handwritten code. Also, I'll be graduating soon, so if you have any job opportunities, that would be great. Thank you very much.
All right. Questions? So are you aware of the work on conformance testing?
Yes, in conversations, I call this conformance testing to some extent, though I might not know the example you mean. Is there?
So for conformance testing, imagine I have a state machine like your TLA specification. I will generate inputs and then get output back to check whether I'm in the expected state or not. And I keep doing this, traversing the state machine. And then if I have reached a state where I'm not supposed to be next state, I will report a bug, kind of, sort of.
Okay.
I'm wondering if you, how do you compare in terms of performance? And the way I see this is if you do conformance testing, you have to cut up your system into 2 pieces. It's almost like client server. You have a state machine of the other part, and you act as another subpart, and you interact with it to see whether you conform it. But for you, you do a monolithic trace modeling.
Yeah, with all the pieces instrumented, yes.
Yeah.
So I would say the key difference here is, in this case, we focus on solving for partial or ambiguous inputs or results. So if you have, for example, you're not sure the order you did things in, or you're not sure exactly what the value of variables were, this has abilities to tolerate and solve for those, whereas perhaps normal conformance testing is more of a strictly instrumented setup
where you control the inputs and then look at the outputs.
Yeah.
I haven't actually tested any performance comparisons with this, but that is interesting. I should look into it. Thank you.
Yeah, all right. Thanks, speaker, again. This is our last talk of the session, so Dustin will tell us about verified compilation for modular meta theory.
Thank you. Okay. So I'll tell you about the work that I've done on verified compilation with some great undergraduate researchers, Gabriel and Ritam, and my advisor, Adam Chapala. So this work sort of came out of a couple of core questions. How should we define language extension, and how should we define compiler correctness to be compatible with it? In terms of what we did to achieve this, we built up a meta theory for combining language extensions and compilers, and an inductive characterization of what correctness means for cross-language translation. And to demonstrate our system, as a case study, I built a multi-pass compiler for system F with recursive functions, existential types, and a global heap. And the interesting thing, of course, is that this can be built incrementally, starting out with STLC and adding features. So in terms of thinking about what definitions we want to think about how compilers are verified. And so whatever definition you're choosing for compiler correctness, whatever relation, you're probably thinking about some kind of relation between source programs and target programs. And I'm using the semantic brackets here to indicate a compiler. And the relation is probably proven by induction over your terms. So you'll have a case like this, for the, let's say lambda here, and each other piece of syntax. And those cases will depend on their inductive hypotheses. And what we really want is we want to be able to talk about what happens when we add new features. So let's say that we want to add recursive functions in. So this fixed feature here is like a lambda, but it has a name that it can use to refer to itself, f. And if we want to add this into the language, ideally, we should be able to just add another case to our proof. Add in the case that looks like the one for lambda, but it's for fix. And what we'd like is if we can just verify this case, then great, we have a verified compiler again. But there's a big question, which is, what about all the other cases that we wrote up before? We're working in a different language now, and are they still valid? And this really depends on how we define correctness. So to give you an example of what can go wrong, let's talk about contextual equivalence for a minute. So contextual equivalence is when you define your program behavior in terms of plugging it into a larger context. And so two programs are equivalent if for any context they give you the same result. Now let's think about this program in the framework of contextual equivalence. This is a very simple little function here. It takes in the function f and an argument x. And it evaluates f on false, drops that, and then just runs f of x. So in the simply typed lambda calculus, call twice of fx is contextually equivalent to f of x. Right? We can just pass in the arguments, and then you can notice you have that f of false there. And STLC is a terminating language. So f of false is equivalent to some v. And from there, we can just drop the v. We end up with f of x again. But what about the recursive functions, right? Well, if you add in your recursive functions, you get examples like this. This function f here, if x is true, returns true. But if it's false, it just loops. And so you can see that call twice of f in true isn't going to terminate, even though f of true does. And so what this tells us is that contextual equivalence is not suitable for extension. And what we need is a notion of correctness that's monotonic under language extension. That is, when we add more rules, everything stays the same. All the facts we knew stay the same. So with that framing, let me get into our formalism in Pyrosome. So the core theory of Pyrosome involves languages defined as lists of inference rules. Formally, these are generalized algebraic theories, but you don't need to know about that to use Pyrosome. So we have sort of a couple main kinds of rules. You can write rules like the one on the left, which introduces a new piece of syntax for lambda and gives you the typing judgment. You can also write rules like the one on the right that gives you the equation for beta. And we define equivalence in Pyrosome as the closure over all of the equations defined in a language. So that's reflexive, transitive, symmetric, congruence closure over all the user's equations. And to give you an idea of what the implications are for that, consider this sort of fragment of a judgment here. We're trying to just, again, a very simple example, but just showing what happens if you apply the identity function to true, and you can prove that that's equal to true. Well, as I said, you have the closure operations and the rules. So you can use closure operations like transitivity so that you can break up the reduction into steps. And then you can use rules like the beta rule I showed earlier. And whenever you appeal to a rule, what you have to show is, yes, this rule is in my language L for this judgment to hold. And the great thing about this is that what this means is the only way that our derivations use our language is by membership there. So we can take a bigger language L prime, and this derivation still holds in L prime. Whatever other rules we want to add in, the derivation still holds. And by subset, I literally mean subset of the rules. Now let's get back to compilers a little bit, right? And talk about how we define correctness for compilation. And in Pyrosome, we define that in terms of type and equivalence preservation. So what we're looking for is type preservation, which is pretty standard, but also equivalence preservation, which says that if E1 and E2 are equal in the source language, well, then once we compile them, the results should be equal in the target language. And this is the key property that we use in Pyrosome. And because equivalence is monotonic, all of this is monotonic. And this also has the benefit of being language agnostic. There's no specific language I'm mentioning here. I'm not relying on any features of the language to define correctness. It also has some very nice properties, just reorganizing it here. If I have another compiler with the green brackets, I can compose them, and just by composition of implication, the composition is the correct compiler. And I also want to point out that I'm doing all of this on equations, so this means it's in an open context. And so what that means is I can do linking, and all the results I have are sound under linking with target code. Now coming back to the idea of proof, because really what we're concerned about is how to make proofs extensible. The proofs are a little more complicated this way, because now I'm doing induction on a derivation of equivalence rather than on a single term. But all that really means is I'm adding in a few extra cases, one for each of the rules, the equational rules that the user wrote. So the case for beta reduction would look like this, and it says if you can compile the applied lambda, that should be equivalent to compiling a substitution. So really, this is just a few more cases on our induction. And again, our goal is now, for adding a recursive function, we should just be able to add some more cases in. And now I can get to how we do that, which is a predicate that I call the preserving predicate, which is an inductively defined predicate that's inductive over the definition of the language in the compiler. So we have a couple cases of rules, right? The case where where a rule defines a new feature f, in which case the compiler should have some target term that represents the compilation of f. And the proof goal that preserving requires is that you need to show that target term is well typed, and this corresponds to type preservation. Now, if you have an equation in your source language, there's no new syntax being involved, so you don't have another case of your compiler. But you have one more proof goal, which is to show that, again, the compiled terms, E1 and E2, are related in the target. And the great thing about defining this as an inductive predicate is that if I want to add a new rule to my language, I just add a new case to the inductive. Or I just add a new case to my proof, right? I just call a new constructor of the inductive. And as a theorem, we've proven that this inductive predicate implies the semantic properties I described earlier. So to show a little bit of our case study, I'm going to sort of walk through a portion of the case study compilers. And if you're not familiar with CPS, I would, rather than focusing on the details of the next slide, I would just look at the shape so you can understand sort of what Pyrosome looks like in practice. So here we have the CPS compiler for simply typed lambda calculus. And we have a type translation that translates function types into continuation types. And I use the negation symbol as a type of continuations. So the intuition should be implies false or non-returning function, right? So a function translates into a continuation expecting its argument and a continuation to pass the result to. we compile variables x into calls to the distinguished variable k, which we use to hold the continuation by convention, that just pass x into it. Lambdas are values, so they also get passed to k, and they get translated into a continuation that just lines up with the type signature. And the most interesting case is the application case, which sequences the computation of the function and the arguments, where it evaluates e first and then e prime, calling the result of e with the result of e prime and the continuation. And this is really just using some substitutions and continuations, but it's a little more pleasant to read it with the monadic bind. Now, how do we write an extension for this, right? We have our fixed rule, so we'll just add one more case for fixed. And this case is going to look very similar to lambda. And by preserving, all we have to do is add a case for this and then not shown the beta reduction for fixed. And if we verify those two cases, great, now we have an extended compiler. So we can put together a bunch of components. I also have a closure conversion pass, and I also have mutable references that go through the same pipeline. And as an example of a feature that doesn't require changing the target language, I have let bindings that can get compiled away in the continuation passing cell phase. But this is all simply typed, right? And we also want to be a little more complicated in the type system. So we also support polymorphism, but this is a little different because now we're changing the shape of the judgments, right? Every rule we've looked at so far has this judgment form that says we have a term environment gamma and then a type A. But now we want a type environment delta to hold our type variables. So this means that not just adding rules, but we have to change the rules we have. So if we had this lambda rule before, now we have to add the deltas onto it, right? Now, to handle this, this is one nice thing about having this whole framework of deeply embedded rules, is that I wrote a generic function that just operates over whatever language you give it and indexes all your judgments with a variable or with whatever new construct you want to add. And I verified that this generic transformation preserves correctness of compilers. So what we can do is take that whole prior slide and put it in this big purple box with delta that adds a delta onto all those compilers. And by the theorem, all these compilers are still correct. And now we're ready to add in polymorphism. So we can add universal types and existential types. And the CPS pass for those, we actually only need existentials in the continuation calculus. Some of the talks from Olivia Fest maybe have mentioned some of these things. And then we have closure conversion for that. And we also, I haven't talked about it, but we also include in the paper a small linear case study and a small sort of imperative language, just to give you an idea that not everything is based on simply type lambda calculus. We have quite a bit of variety that the system at large can support. So thank you for listening, and please reach out with any questions.
Thanks, Speaker. Questions? Any questions? Now you use a compiler in your title. So now can I compile down to assembly all the way?
So I have not done that yet. In the near future, I am interested in connecting this to the Bedrock 2 language that we have in our research group, which is sort of a lower level C-like language. And if I connect to that, then that has a compiler to assembly. So I would like to get there, but not at the moment.
Hi, Max New, University of Michigan. So I've tried to work with things like GATS before, embedded in a proof assistant, and it was a little difficult for me. And so I wanted to know how ergonomic were you able to make it to work with these kind of embedded theories?
Yes, so there's two components to that. One is in terms of writing them down, and then the other thing is in terms of proving things about them.
Yeah.
For writing them down, I have a system. Inside Pyrosome, I have a system for marking arguments as implicit versus explicit. And so as long as you mark the right things implicit, you can write things down exactly as you want and leave it to the proof portion to figure out what those should be. As far as the proof portion, I didn't have time for it in this talk. I have a lot of slides from various points. But I have substantial automation that I built for proving things correct, proving the various goals that I have. And in total, in that case study I showed, there's 127 goals that come out of the preserving predicate. 110 of them are proven totally automatically. The remaining goals, I have designs on how to solve automatically, but generally involves things like side conditions that the automation doesn't handle yet. What it all boils down to is it takes a lot of work, But the automation is getting there, and really, with the automation, it's quite pleasant.
Okay. And do you use what do you use for binding, like de Bruijn?
For binding, I use essentially de Bruijn.
Hi, thank you for the nice talk. I have a bit of a high-level question. So I think one big challenge in compiler verification is verifying optimizations.
Yes.
And I wonder how this framework of extensible compiler fit in play with this optimization verifications.
Yeah, so I haven't done a ton of optimization work. I do have one optimization pass in my current compiler, which is essentially a generic partial evaluation pass that just uses the rules of the language to apply what linear rewrites it can. In general, optimization can have a little bit more flexible of an interface, because since you're usually within the same language for automation, or for optimization, you can, instead of proving equivalence preservation, try to prove just that your input program is equal to the output program. And so that gives you some more flexibility, but I haven't really explored the space extensively yet.
Thank you.
Hi, thank you for the talk. I'm wondering, are there any abstraction or languages that you think are particularly good at being expressed in this kind of framework, in this type system?
Yeah, so the generalized algebraic theory framework was originally designed for dependent type theories, so it's actually very natural to express any of those. In general, I would say type functional languages fit it better, but I've also, to demonstrate as an experiment, done some more imperative type things.
Thank you.
Session. We have a word session and some discussion in the ballroom after. Thanks.
Thank you.